99% of the students who are learning GenAI are absolutely doing it wrong. Most of the students who are learning GenAI are actually stuck into the loop. They're watching 30-40 minutes of videos or tutorials around RAGs, GenAI. They're blindly following all the codes, frameworks, and they think that they have mastered it by building a so-called project in just 30-40 minutes. But the reality is they have not even learned a 1% of what this field is. You cannot land a job by just copy pasting the code from other videos and putting it out there, but with different ideas, or probably you cannot even add this into your portfolio project. And you think that this will get you a job? Absolutely not. I've seen tutorials on RAG build a chatbot in 10 minutes, build a chatbot in 40 minutes. Do you really think that you can learn to build a chatbot and still get to know about the foundations or the production skills and all those things? Let me be very clear on this. You cannot even get to know 1% of the foundations. Forget about the production grade skills which you need for this domain. While there are immense opportunities into this field, I have seen so many of my students grabbing a very high paying job just because of this domain, but they were doing it right. Now the problem is very simple. Most of the students are talking about how to do this. That's it. They are not talking about what, whys, and underlying principles and details, foundations, and core towards it. And that's the main problem. And that's why I come up with Complete GenAI RAG Systems course. And we won't teach you to build a particular cool application in just few minutes or few hours. We will first of all start by teaching you the core concepts and the foundations, which will give you the why answers for most of the things which you'll be doing into the projects, so that you know better than most of the people the inner workings towards it, how exactly all these systems are made, what are the intuitions behind it. And that's what I call this core. And I have seen even those videos which teaches you about tutorials, they are literally building a basic system. They are not even building the production grade systems. While we teach you the core, we'll also tell you how to build production grade systems which will help you to be a professional into this field. The first step is that we truly learn about foundations and the core of the NLPs which will be used into the RAG systems. So you can find the syllabus in the description box below. I've written all the things which you'll be learning throughout. And then we'll work on some of the projects where we'll be utilizing all the concepts which we learned into our foundation and then try to bring that into RAGs. And then we'll be using advanced applications like PGAI, pgvector scale, as well as PGAI vectorizer, all these interesting libraries to build our production grade applications, as I said, which does not only works for demos, but also works for millions and millions of data out there. And you'll find the first sections of this will be theory, but it's not about theory. We have a hands-on. As I said, we start with first of all building a Q&A system, which is taking the concept which we have learned and then implementing it. And then we'll be working out of very first project, which is LexiChat. And LexiChat is nothing but an application where you can upload your documents and have the conversation with that document. I hope that this video will find you well. All the installation guides, first of all, I ask you to watch all the installation guides first and make sure that you have the system set up, and then you get started with the course. I'll catch up with the tutorials in the next ones. Thank you so much. So now let's get started with the course.
So hey everyone, welcome to the first module into this module. Into this module, we'll specifically cover the foundations in NLP. So we have originally started with covering up some of the foundations, because these foundations will eventually make your understanding of RAGs and other concepts very clear. And when we work on our major project LexiChat, we should be able to understand much more in depth, and instead of just learning from upper way, you will be able to learn something in more foundational, because I always say that core is very important instead of just you learning how to write a couple of lines of code. So we'll focus on the little bit of foundations. We'll not go too much into mathematical details and all, but still I'll make sure that you truly understand what exactly each process and steps are. You don't really need a lot of big mathematics background for this. It's just that we'll be covering very much in detail about text processing, tokenization, embeddings in this module 1, and then we'll be covering several other modules for the same. So let's get started with eventually a story is, why do we need natural language processing? I know you have been coming from several NLP background and you already might know about this, but for the people who don't know, I want to take a very simple example. So let's say you're a detective, you want to analyze thousands of witness statements in a big case. Now, so you have a lot of statements, like you can see in the image, a lot of kind of witness statements, and they all are in raw and unstructured format, and you have very limited time to find key patterns, name of the suspects, locations, and perhaps connections between people. So basically, you have to make sense out of all these witness statements. So let's say that if you take all these 1,000 witness statements, you go step by step and you read each statement very manually, it will take you forever. So human thought, okay, what if computers help you to do this? Computers help you to find patterns, find connections between text, and probably find insights from the text little faster. So that's where the idea of NLP comes into the place. But now, let's say that the computers becomes your investigative assistant. Let's take an example like that. So the only problem with it that it does not understand the language like humans do. It will not understand like the text written out there just like the humans does. It sees words as strings, like you know in a programming language you have something known as strings as a data structure. So it understands that as more as a strings instead of just what exactly we do. So for the computer to help you efficiently, it's need a way to break down each statement into manageable chunks, understand meaning, and then connect the dots across documents. So it needs something in a way that it like what can you say, binary language, so-called binary language, to fully understand. So it really needs a way to break down each sentence into computer understandable language. We'll talk about what those understandable language is, but it needs a way to find to make it in a format the way computers understand. So what is the way for the computers to understand the text? So a computer, to help computer understands these texts and help you to solve some witness cases and then possibly make patterns, make insights and all these things very efficiently and productively, is computers need three steps. I originally classify into three steps. The first step is processing of the text, to make sure that we are only feeding the right information, the processed information. So if you're coming from a machine learning background, you should be knowing it very nicely that before you feed in the data to be trained onto the model, you first of all process it. And that's what you do it over here, that you first of all process the text to make sure that the irrelevant texts goes and only relevant text goes to your computers. Then the next step which comes into play, which we call as a tokenization. So as I told that your whole documents needs to be broken down into a manageable chunks. That's what the tokenization means. And then once that is broken down into manageable chunks, it has to be converted into a language, like a binary language, in order for the computer to understand. That's what we call as embeddings. Our whole concept in RAG will revolve around tokenization, embeddings, and all these three steps. There's no other steps which will focus on other way, but now let's try to expand each and every step of this, like text processing, tokenization, embeddings. And if you don't understand this, don't worry. Eventually you will get it over the period of an hour which you'll study. But one thing I want to make sure that we'll continuously keep on revisiting the topic and make the good storyline out of it, so that you try to connect how these things eventually help. Because a lot of people eventually jump to just RAG tutorial and they learn in 17-20 minutes. It does not really help. That's why this course is pretty long, to help you go step by step from starting, so you understand each and everything. So let's first of all go to text processing. So if you're coming already from a NLP background or some machine learning background, you should be knowing how does this really helps. So text processing, what does it really mean? It starts by prepare the text by lowercasing. So whenever you get some sort of document, you lowercase it, or probably you do some processing like you remove some punctuation or you remove stop words. So stop words are those which does not really adds any value, like common words like the, is, in. They do not add much meaning to it. Of course, they may add some grammatical meaning, but the, is, in does not really add such a value or the meaning to this sentence. Punctuation, removing punctuation, that's one of the processing areas. Another way is that, so we do lowercasing. The reason why we do lowercasing is, let's say that you have two quick word, and one quick is in lower word and one quick is in the uppercase. So the computers, to make sense that this is the same word, you just lower cases, so that the computer will not take the same word but differently. It will take the same word same. That's why we call this lowercasing all the sentence. So it's basically to ensure, let's say, a hello in a lowercase and hello in uppercase are treated as the same words once we do the lowercasing. Then we do the stopwords removing, and then there's one interesting step known as stemming and lemmatization. So what does it really mean? Stemming and lemmatization means that it reduces your words to the root form. So let's say that you have quick brown fox running. It will make the running to run. The reason why it does it is because we want to make sure that all the added grammatical things gets back to the root form, so that anything, let's say running and run, will be considered different. So what we do, instead, we cannot do anything with run, but we can do something with running, so we apply stemming to it, so it converts back to a root form. So I want to show you how does it really looks like. And this is, by the way, stemming. So you have let's say you have a paragraph where these things dog changes with their time, with the changing stuff. So they have they all mean that, to be honest, same, but it really is different grammatical stuff. So stemming will make this to a root form, so all the changes convert to chang. That is, stemming is little harsh. So the difference between stemming versus lemmatization is stemming sometimes may give something which is not known. So it just make backs to the root form, like this change when you're forgetting the e. But lemmatization is little more flexible and makes sense of the words it changes to. So over here, if you see change, so stemming or lemmatization based on the context. If you have too many, if you want very stricter guy who just makes the to a root form like hell, that's what the stemming is, and otherwise lemmatization is one of the form. So let's go to one of the practical example I really want to showcase to each and every one people out here is, we'll start. So I've actually taken some of the reviews. I absolutely love this product, all these things, and I converted this into a data frame, which we call this as a review, and then the column was review. And then what I did, the first step is lowercased it. So I simply taken a data frame and that particular column, and then lowered it and created a new, so that you can see it. So you can see that I actually love this product. It's super. Actually converted into all these lower cases. And then the next steps which goes in, that you go ahead and remove the punctuation and emojis, irrelevant punctuation and emojis. Of course, see, sometimes emojis adds a really good value. So what you do, instead of removing emojis, you eventually go ahead and make sense out of emoji. So that instead of having an emoji, you just say, what is the meaning of that emoji? There are several libraries available to convert a particular emoji into a particular meaning. So for example, if it is 2 emojis, so 2x happiness would be written out there. So of course, over here, for the simplicity, we are just removing emojis, but emojis truly add a great value. So you just go ahead, you remove the emojis and punctuations and all, and then you go ahead, and then that's where you see that all these things are removed. And then you go ahead and remove the stopwords. So we use something known as NLTK library, and then we download the stopwords. So stopwords there are a lot of stopwords. So NLTK provides a corpus of stopwords, which you can see out here, that there are a lot of stopwords which you can see. And NLTK gives a corpus of stopwords. So we download those corpus of stopwords, and then from the corpus we just import those stopwords. So we take out this corpus of stopwords which are in English, and then we say that okay, here we go. If find out the stopwords and remove it, or possibly it is saying that make a new column of review no stopwords and removing every stopwords out from there using list comprehension and all. So but you can see that it removed it removed this, it removed its. The reason why it removed, because it does not really add a value. So absolutely love product, super efficiently running. So it's more like processing as much as you can do so that your computers does a good job or gets a good data in it. There you go with stemming. So stemming means, as I said, making it back to the root word. So you use NLTK library and use the Porter stemmer. You can use the lemmatizer too. So you can see this absolute has been converted to this love product super efficient. So you see absolutely got converted to absolute, right? But stemming is little harsh. That's why the word is not making sense. If you use lemmatization, it will convert this to absolute. So these are few of the text processing techniques I would love you to know. And what you can do, you can go ahead, use several libraries, make sense out of it. I'll also link some of the resources for you to explore more about the text processing. Now the next step comes in. Now once you have the good data, once you have the good text data, the next step is to break it down into chunks so once the text is clean, we need to break it down into smaller pieces because as you see, if you have a big problem, convert it to a small pieces. So typical is like if you have a sentence, you convert this into words so that the computers can go to each and every one of them and analyze them individually. So we'll go ahead and talk about the tokenization and embeddings right now. So now the next step is nothing but known as tokenization, right? So what does tokenization really mean? Tokenization means once your text is clean, we need to break it down into smaller pieces, which is typically into words or subwords, so that the computers can go ahead and then analyze them individually. So let's say that you have quick brown fox jumps. You have a tokenizer. So tokenizer will convert that into several words, like a chunk, right? So what does it really mean is it splits the sentences into words or a smaller units. So it's like a indexing, so it's like a basically converting a bigger sentence to a smaller sentence so that your computers have a very easy time to go through each step individually. So let's go ahead and find out some of the practices around it, some of the uh, Colab notebooks, some of the practicals which we should do is why tokenization is needed. I think I'm big fan of anything you do it. You should first of all know what, why, how, and all these small questions. You'll truly get a concept. So why tokenization is truly needed. As I've written into this Colab notebook too, for a computer, the sentence I love NLP is simply a string of characters without any inherent meaning. So what do, you truly convert this into a smaller subparts so that computers can go analyze and compare and perform operations on. So it's typically easy for them to know about breakable sentences instead of a long sentence out there. Now, the next is contextual understanding. So, tokenization allows models to handle words, subwords, or even individual characters meaningfully. Even if you have the emojis, it will have its own relevance towards it. So eventually that really truly helps. I know it might not make sense too much of why we are doing tokenization right now. It will make sense if you truly go to model number 2, 3 and all. It will start making sense to you. So how tokenizers actually work? Very simple. Let's say if you use tokenized one of the NLTK library again and use word tokenize, you can also do sentence tokenize and all. I don't like NLP, so it will converts into this tokenizer. It uses that tokenize and converts I do not like NLP, and even the punctuation has its own relevance out here. That's why we need to have it, the tokenizers. And then there you have several other tokenizers, which is subword tokenizer, which we call this as a byte pair encoding, BPE, which handles uncommon words and language variations more effectively. So there are a lot of tokenizers. If you truly find there are a lot of trained code tokenizers by Hugging Face and all these libraries, all these big giants like Google and all, the foundations is set by tokenizers because a model needs to know how should I split a particular sentence. One might be via just spaces, but that shouldn't always make sense because over here the spaces are not there, but still it is able to. So subword tokenizer, what it does is it splits unhappiness into unhappiness. So allowing models to recombine subwords and understand them into a different context out there. So that's why we use subword tokenizers, byte pair encoding. Another one is sentence tokenizer. So sentence tokenizer means we split the text into a sentence rather than words. It is not rarely used. It is very rarely used. I have rarely used it. Uh, but there are a lot of companies who still use it. So the stock tokenizers are nothing but breaking down text into chunks. There are several ways to do it: words, subwords, sentence. It should make sense, right? So this is the about tokenization and all. Our next is, so let's say once you have processed the text, once you have broken down into manageable chunks so that the computers could understand, but even though you have broken down, it's still a text, it's still a string of text in a list. So what you truly do, you have something known as embeddings. So what is embeddings? Embeddings are nothing but it's like a what you can say. You represents the words as a numbers so computers can understand similarities. So if you know about one hot encoder, so one hot encoder, what it does, it converts your text, a categorical feature, by creating a new column and then stating whether that feature was available or not for it to make sense to the models. The same way embeddings work. Embeddings are nothing but you represent a, so let's say man, woman, king, queen. So these are the what can you say? Kind of a tokenized vector. So every word into that will have its own relevance. So man with a living being will have 0.6. Feline, it's way away. Human, yes, it has a more similarity. So it is converted into an understandable numbers. So that's what we call as embedding. So like kind of a vector. So we'll talk more about a vector database, embeddings and all in more detail in a bit. But it basically turns the words into a vectors. And if you see over here, that similar words like king and queen will be more closer than any other over there. For example, man and woman will be more closer, so their vector will be more closer to each other rather than what can you say, other words. So let's quickly go back to our embeddings. So how you can think of embedding is that it is a way to represent words, the tokenized words, each and every word over there, so that the computers can understand the meaning and find out the relations between them. So let's say that each student in your class has a different traits like height, hair color, or favorite subject, and each word has a different meanings or traits that needs to be represented. So let's say I would like to take one example. So imagine you have the words like king, queen, apple, banana, and let's represent each word with these three traits, which is royalty score, fruitness score, and gender score. So these are the three traits. Just like you rate a student based on their strength, speed, and agility, you actually rate these based on these three traits. So king will be more inclined towards the king and queen have a high royalty score. Apple does not really relates to these uh, royalty score. So if you see the similar words king and queen have a high royalty score, so that computer knows that they are related in terms of being royal. But apple and banana have a high fruitiness score but low royalty score, so they are recognized as a fruit, not a royalty. You can also see the gender differences: king 1, queen 0.5. Apple banana does not make sense. So the embedding is nothing but they create a sort of a vector with some traits out there, and you don't have to worry about every time about how we'll do this in a real data set and all. Do not worry about that right now. Try to understand why embeddings are created. Embeddings are created because of very simple, because we want to make sure that computers understand the word based on their traits. For example, king will have a high royalty score. So traits needs not to be always defined. That has to be trained. We'll talk about how these models are trained later on in a very brief way. But embeddings are nothing but a set of vector databases. So what can you really do? Let's say if you ask a computer to find a word similar to the king, it will look at the numbers, vector, and whoever is whoever is close to the king, whoever is close to the king vector, whoever word is close to the king vector, it will show that queen is so close because they both have a high probability scores. So these are one of the few examples. So there are several ways. So there are a lot of algorithms available right now who convert your text data into embeddings because they're already trained enough to represent these words. So one of the algorithm is known as word to vec. We'll not go into architectural details on how it is created and all. These are for research purposes. We are learning RAG. So we'll just focus on, I want you to just know word to vec is nothing but an algorithm which can help you to make meaningful vectors, because you cannot just put any numbers into it. It should be meaningful. Like king and queen should be close when man and woman should be close. So we train the word to vec model, first of all, on these sentences, right? And then we get the embedding. So embedding for the king is this, right? And then what is the most similar words to the king? So we find, using the model, we find the most similar, which is king, queen, fruit, man, and apple. Of course, it has disparities, but you can see the queen is first. So king is to queen. So it has the highest similarity score between. We'll talk about how these similarity scores and all these things are created. For just now, I want you to focus on understanding the core idea behind embeddings. We'll talk more in detail over the period of time. So if you plot this into higher dimensionality, you see king and queen are closer to each other. Of course, we have limited data set, so it has not been performing very well. But this is how it looks truly over here. So if you have used something known as one hot encoding, so one hot encoding, what does it really do? It simply goes ahead and then takes your categorical, creates a new column, and then says 1 0 1 0 1. So if you have 100 categorical variables, it will create 100 no more columns. So higher dimensionality, higher, more complex. There are a lot of issues, and there's no semantic meaning. There's no relationship between words. There's no relationship, but over here there is a relationship, and because we are putting some embedding into it, so there is a relationship. That's how we are able to use the traits to find out king is to queen, apple is to banana, man is to woman. So it's like that. So embeddings are nothing but converting your words, tokenized words, into a set of vectors, meaningful vectors, which when compared, which represents the relationships between two words. So this is a small overview about embeddings. What next we will do is we will talk a little bit more in detail about something known as attention mechanism transformers, and you will see how these three steps of processing, tokenization, and embeddings are always coming into the place, and you will get more understanding about it in a bit.
So now we will go ahead and talk about attention mechanism. So in the last couple of topics, we eventually went through the three steps, which is useful for the computers to make sense of the language. So we process the text, we tokenize it into manageable chunks so that computers can go and see the words individually, but still the chunks are still string of characters. So what we really do, we convert those words into an embedding. So every word will have its own vector representing its meaning, and embeddings can be several embeddings. One of the algorithm which I shown, which is word to vec algorithm, which converts that words to a particular meaning out there. So we'll not talk in detail about how this training process looks like and all those things. I want you to get a core architecture of it, core idea of what exactly these attention transformers or embeddings are, so that when we go to RAG, you'll be able to understand them much more in depth. So it's attention. So now once we have the embeddings are nothing but a set of vectors given to a particular word to represent the meaning. Now, once you have those words, now let's say that you have a whole new document of 1,000, 2,000, 100,000 words. So you'll be having 100,000 vectors. So if computer needs to make sense of it, they need to go to each and every vectors out there and then try to understand it. Now that's where the problem arises. The problem is, let's say that you have a long sentence, which is kind of a 100,000 words. So what you will do, you will eventually go ahead. The computers needs to go ahead, go through each vectors, which is an embedding of a word, and then try to make sense out of it. So I want you to look at one of the example. So let's say the chef who was famous for his delicious pasta quickly prepared the dish for the guests. So as a human reader, personally, I just focus on the main point. Say, okay, the chef prepared the dish for the guest. So the main point over here is the chef prepared the dish. That's what the human reader will do. If you're given a document, you'll have the main point from that document instead of you going to the each word, even the and everything, and forgetting the main point. So, details like, as you stated, that over here, famous for his delicious pasta, will add some context to it, but are not essential for understanding the main action, what has been done. So, you will not every time go to your dad and say that, I mean, the chef who was famous for delicious pasta quickly prepared the dish for the guest. Does not make sense. The main point is the chef prepared the dish. That's it. And details like famous does not really add so much of value or the main action towards it. So just like this, when computers process text, when models process text, they struggle with their selective focus, which means that they tend to give equal weight. So for them, the chef would have the same weightage. Who was famous will have the same weightage. So every word they give an equal weight to every word, which makes it hard for them to focus on what's really important. So if you take let's say you have several words out here, and you give every word an equal weight, you pay more attention to every word, you will forget what the main point is. So humans will automatically focus on the main point, but computers struggles because it gives focus to every word into that sentence, which makes them really hard to know what's really important. So, how does this? There's something known as attention. So, attention solves this problem by helping models focus on the critical part of the sentences. Just like how a human pay more attention to the main points when reading, right? You have a one chapter. You have few main points from that chapter. So, to give that capability of focusing on what's really important and what's really matters a lot, that's what attention mechanism comes into play, and that's where attention we the concept of attention comes into the play. So what is attention? It's a process that helps the model decide which words in a sentence are most important into a specific context. So it's just like it helps computers to know what is really important into that particular sentence, into that really specific context. So it's like giving each word a weight that indicates how much attention it deserves. So let's take one example. Let's say that you have the cat which was sleeping jumped over the wall. So words like cat and jumped get a higher scores because this explains the whole meaning. It says cat jumped, which is the main important point. Now, let's say if you're trying to understand who is performing the action, the model might place more words onto the so let's say that you want to understand the main course of action. So the chef prepared, over here it will be more the chef and the prepared. So the weightage would be given to these important words, and less weightage will be given to famous, or delicious pasta, because they are not they do not add much. What can you say? It's more essential for understanding what was the action. If your task is to understand the action, right? So it's more like that. Uh, it assigns, in a sentence, attention assigns each word a weight of how important you are into this particular context. Right. So higher weight means more attention, lower weight means lower attention or less attention. So in a simple terms, it helps the model zoom in on words that matter the most for the task. For example, if you're translating a sentence, it focuses on a most important word. If you're answering a question, it just takes from a big question. It takes, okay, this is the question, that is the question. Okay, I will use these two important words, more weightage words, to find out my answer. So it's basically zoom in into the one words that matter the most and then try to find the task. So
let's say that you have 100,000 words embeddings, it will only focus on few hundreds who has the higher weightage instead of focusing on all those 100,000. Because that is computationally expensive, hell lot of issues, and all these things comes into the play. So I don't want to go into more detail about the architectures, encoder, decoders, and all those things, but I will just quickly skim through how exactly it works, the attention. And then when we go to transformers, you will see how attention builds up to transformers. So attention, how does it really work? So I want to classify attention to two different steps. The first step is it assign importance to the words. So, when processing a sentence, attention assigns each word an important score, which shows how much each word contributes to the meaning into the current context. So, let's say that in this example, the cat which was sleeping jumped over the wall. If we want to know who jumped, the words cat and jumped would receive higher attention scores, and instead of which was sleeping over the wall will receive lower scores because it does not really relate to the action of jumping. So if you ask who jumped, is cat jumped. So cat and jump will have a higher scores while rest of them will have a lower scores because they do not really direct with the relate with the mean with the action of jumping into this particular context. So that's the first step, is assign importance to each words. Then calculate attention scores. So the model calculates these important scores based on the relationship between words. So as I told you in embedding, king and queen are more closer together. Man and woman are more closer together because their vectors have the similar meanings. So the model calculates the importance, scores based on the relationship between two vectors or embeddings. So words that are more closely related in meaning or action will have a strong connections or higher scores. Because if you talk about who jumped, cat and jumped will get a higher score because they are directly related to each other. And wall will also have a moderate relationship with jump because it tells where the jumping happened. So if you truly see, it involves in practice it involves some maths. As I told, I don't want to get into too much detail about maths and stuff at this particular point of time, but the goal is to figure out which words influence each other the most. So it's nothing but giving or finding out the relationship between two words, and if there is a higher relationship then you give the higher scores, if the moderate you give moderate scores, if there's low then you give the low scores. If there's a cat and dog, it will be together, but into this particular context it will be far apart, right? So that is the step number two, is once you give a importance, then you try to use that importance to figure out the relationships between the words, and then you adjust the focus based on the scores. So after calculating the attention scores, the model adjusts its focus to give more importance to the higher scoring words. So instead of treating every word equally, what model really does, the model focuses on the words with the highest attention scores and use them to interpret a meaning. So what does it really mean? Is it adjusts the focus. So as we go along, it adjusts the focus to starts focusing on the higher scoring words. For example, if you chat with a GPT, it understands your context, right? So it is adjusting the focus on the way. It is not what can you say? It is not having the same scores. It is if you are asking a one question and then you're asking a different question, so different question will have different words, so those words will have its own now the GPT will start to focus on those words. So it basically adjusts focus on the scores out there. I hope that it makes sense. Now, this is how the attention works. So, attention is more like, let's say that you're in a class and teacher is explaining an important topic. So, when the teacher talks, you might pay close attention to the key points because they only talk about the main ideas from the chapter. They ignore small details which does not really add much value. So the same way attention mechanism helps the models slash computers focus on the main idea within a sentence, like who did, rather than getting stuck on every word out there. right? That's why the attention is pretty important into this analogy. I want to take some of the examples of attention mechanism. So in machine translation, let's say how attention has help in a context like machine translation. So you might be using something known as Google Translate. So into this, you focus on the specific words in one language and finding their more important equivalence in another. So it's basically you focus specific words into one language instead of going through every word into that particular language. You focus on it. In question answering like GPT, models can zoom in on in the part of a paragraph that has the answer instead of reading everything equally. So let's say that you ask, what is data? The GPT will have its own set of two, three paragraphs. So instead of going through each word, it just zoom in into the particular answers over there and tries to get you the uh, answers. Same goes with text summarization. So attention helps to summarize a text by focusing on key points rather than every sentence. So when we do our project on LexiChat, you will notice that how well a model takes the particular whole big document and eventually goes ahead by answering your crisp question. And now you will be wondering how this is possible. That is possible because of attention mechanism, because it helps to focus on important words in the main parts of the sentence, which assigns weights to the words based on the importance in a particular context. And attention scores are calculated based on relationships. King is to queen, man is to woman, based on the relationships, and guiding them to focus on the important and the keywords. So that is why I wanted to go a little bit deep into the attention mechanism. I hope it makes sense to you. Now we'll talk a little bit about how we can use the attention mechanism to build more powerful NLP systems, and eventually how we eventually come to models like retrieval models and generative models over there. So now we come to the another major aspect known as transformers. So before going on to transformers, I want you to realize that any topic we are studying three main such things: why, what, and how. Or we can say what, why, and how. These three main ideas into every topic so that you understand it fully in depth. So I want you to think about a problem. Uh, Into the attention mechanism, let's say that you have your tokenized text and then you have the embeddings. Attention mechanism help you to focus on um, what do you say, each words. Attention mechanism helps you to focus on the words which are really important based on the context. Now tell me, how will the model know which words are important based on the context, right? So how will models know about the context? So let's figure out that the cat jumped over the wall. That is a sentence, right? And for attention mechanism to know what is really important, you need to know the full context, which is the cat jumped over the wall. So if somebody asked who jumped, cat jumped. How jumped? Over the wall. So the models needs to know the context. Attention does not helps in context. Who helps? Transformers helps. And that is the another problem which arises, that how to make models understands the context in one go. It's like that. So I want you to understand a story, which is, let's say that you read a long novel one word at a time, right? Without being able to look back and forward, it would be tough for you to understand the full context. So if you are having 100-page novel, you're reading one word, you'll be like, let's say you are reading a story. It's like that. So if you read a one by one, you're not able to understand it, right? So this way, what you do, you go ahead and understand the whole context like a human, right? So this was a problem for older NLP models, which rate sentences like the cat jumped over the wall one by one, word by word in a specific order. So as soon as somebody reached to the 10th page, the model reached to 10th page, it forgets the first what it read. So it was not having the context, as I told, that even attention mechanism needs something which can help you to understand the context better. Then only attention mechanism will work, otherwise it will not work. So instead of reading one by one, transformers helps them to solve this issue by letting the model see the entire sentence at once. So the instead, so transformer will see the cat jumped over the wall, and the transformers will help attention to transformers will give the context to the attention,
and attention will see all the words inside it. Now, uh, basically, they don't process text word by word. They can capture complex patterns and relationships within a sentence in a language without losing a context. So instead of looking one embedding, which is the words embeddings at a time, it looks at entire embedding at once and gives the ability to the attention models to focus to find out the important words from here. Right. So before transformers, it was hard for the computers to remember the details which had appeared in the earlier in the sentence, understand the complex relationships, or process text quickly. It used to take a hell lot of time. So transformers change this by letting models see the entire sentence or a text at once, which means that they pick out the most important words one at a time and understand relationships even if the words are far apart. The cat over the wall. So they are far apart. And process text much faster, much easier than what they could do. So let's say that you're reading a sentence. The lion, tired after hunting all day, rested under a tree. So without transformers, the model might forget the word lion by the time it reaches the rested. So with transformers, it can remember that lion and rested are connected, even though there are the words in between. Right. So it eventually helps the attention mechanism. It eventually helps the attention mechanism to focus on the important parts of that text and capture relationships between the words, even if they're far apart into a sentence. So I hope that makes sense about what is transformers and why do we really need, because to understand a context or see the sentence at one go, otherwise it used to take a hell lot of time, and the problem which was coming is people the models were forgetting by the time it was reaching to the end of the sentence. So it sees the whole story at one glance and uses attention mechanism to find the key ideas immediately and capture relationships between the words out there. That is what the transformers are. It's pretty simple. I don't know why people think it's too hard. It's pretty simple. It's like a looking at everything. So if you understand a thing via a story, you will get it much easier without too much in mathematical details. So how it works, because as I told, we'll talk about why, what, and how. So, how it works, the first step is that you represent the words with the embeddings and the positions. So, as I told, the words has to be a string of characters, has to be converted into an embeddings. So, if you see the dog chased balls, so every word, of course, we have not done text processing over here. That's why the is still there. Um, so basically, it is converted into a numerical representation, which is a vector embeddings, which we will talk about vector embeddings, vector databases in a bit. But over here, you convert the words into a set of numbers and embeddings that represents the meaning of the word and which captures the relationship, right? Which captures the relationship. And also you add the position to the number to each word to keep track of order of the sentences. Otherwise, into the model might forget which is the order. So though you also add a position to each and every word into that for that particular sentence. So the position number tells the transformers where each word in the sentence lies. So it knows the order is the dog chase the ball instead of ball chase dog B. So it shouldn't happen like that. So the step one is you make the words into an embeddings by giving the positions to each embedding where it lies into that particular sentence. And then you use attention to find important words. So then the transformer then uses attention to determine which words in the sentence are the most important to understand the meaning. And attention scores tells the transformers which words relate most closely to each other. So it's more like that you use attention to determine which words in the sentence are the more important, and then you use attention scores to tell the transformers which words are related to each other. So let's say that in the sentence, the dog tired after running chased the ball. Now, here, dog and chased are directly related, while tired after running is an extra information added. So, attention helps the transformers focus on the dog and the chased because they tell the main story. Now, if the question is different, what dog chased, then the attention scores gives dog chased the ball.
That's where the score will be high for that, right? So every context, every question will have its different attention scores, which tell who are closely related to what. So let's say that when you have a model asking, yeah, you are asking who chased the ball, the transformers will knows to look at the dog and the chased and ignore other details because they have a higher attention scores, and they are closely related to each other, right? And then the next step is you use the attention to find important words and use attention scores to group them. I mean, to know which words relate most closely to each other. Then step three is you layers. Transformers have layers, each one refining the model understanding. So imagine um, a group of detectives trying to solve a mystery. Each detective specializes in finding certain clues like fingerprints, airlists, motifs, and all those things. So you're a group of detectives and you're trying to find some certain stuff to solve a mystery. And in every detective into that particular group will have its has its own speciality, fingerprints and all, because as you see even in other shows they have it. So they build a full picture of the case. So together, one may be good at fingerprints, one may be good at motives, one may be good at understanding some certain clues. So together they build up a very strong case, full picture of the case. Same way, each layer of a transformer model adds a new level of understanding until the model has the complete idea of sentences meaning. So let's say that in the first layer, the transformer might look at the basic relationship like connecting dog with chased. But in the next layer of the transformer model, it might understand that chase the ball is an action happening because the dog is involved. So it's more like that every layer of transformers will improve the understanding of the model better and better. So each layer is like a filter that focuses on the different aspects of that particular sentence. That's the step number three. Step number three helps you to refine the model by having more layers, because a single layer might know, okay, dog chased the ball, which is dog and ball. Next sentence would be what they chased, how they chased. So all these layers will make it easy for the models to really understand the whole context in here. And then you go ahead and then you have several examples. So let's say the Google Translate. So Google Translate is how does transformers are heavily used in Google Translate. They understand how words relate across languages, so they can translate phrases accurately even when the sentence structure is different. Transformers can allow chatbots to know what you're saying and respond naturally. So it's like if you type tell me a joke, the Transformers focuses on the important details like joke and responds with something funny and ignored another unnecessary details. So all these are a few steps to know about transformers. So I hope that you're getting a story that how embeddings are very useful, right? And how attention helps you to build a better, and how transformers builds you to solve a specific problems while dealing with texts. So I hope that this really makes sense. In the next one, we'll talk a little bit about text similarity, because that's another major concept which we'll talk about in a bit. So now we'll go ahead and talk about something known as text similarity. So what is text similarity? So it's a way to measure how much two pieces of a text are alike or related to each other. So I want to tell you a story. If you remember, I was telling that attention scores will tell you how two sentences are equal, are I mean closely related to each other, right? So we used to say king is to queen, man is to woman. So their embeddings were closely related to each other. By seeing a plot, you can see it, right? But how can you do this mathematically? Because I want you to get a really understanding of how does this happen when in code and all. So it's basically similar to, let's say you have a two sentence, and every sentence will be tokenized, will be into words, and then it will be converted into embeddings, right? So let's say you have a two sentence. I love to play basketball and basketball is my favorite sport. So how does the text similarity helps? So text similarity measures helps computers understand this relationship by assigning a score to show how these two sentences are related to each other. You can also do for word similarity.
Right. So let's say that if user asked a question, who played, what is your favorite sport, then similarity scores will help you to locate a text that's more closely related to that question. I wanted to quickly go ahead and tell you about it. So I want to talk about something known as cosine similarity. So cosine similarity is nothing but helps you to get relationship between similarity scores between two words. So let's say item one is man, item two is woman. So it will tell you the score between two of them by taking out the angle of it. I don't want to get in more mathematical details. I want you to understand this via an example. So let's say you and your friend are each holding a flashlight. If your flashlight is in the same direction, let's say in a north, so your paths are similar. So you'll be having the higher similarity score. But if your flashlight is in different direction, your friend is in different direction, then eventually your similarity score will be different. So cosine similarity, what it does, it measures the angles between your two vectors. I hope that you know how to plot a vector into two-dimensional vector or into a x and y graph. uh, it eventually finds out the angle between two text vectors, and it shows how similar two pieces of text are by comparing the direction of their meanings rather than the exact words. So if your item 1 is into the north and item 2 is into the north, they are similar, like they're facing the same direction. But if the one vector is in north and one vector is in this another direction, then it is not similar, right? So the cosine distance will be high. So cosine similarity is one way. So let's say if someone asks, tell me about basketball. So what it does, cosine similarity finds sentences about the basketball by comparing all the angles of the vectors that represent those sentences. So it will pick the basketball using attention, and then it will find all the vectors which are closely related to each other by finding out the direction. And if they're facing the same direction, then it shows the results relevant to it. Right. So it's more like that it considers the overall meaning by taking the direction instead of going through each word. So if you want to say, so it just say, I will match your each sentence to the sentence. If it is 100% match, I'll give you 100% match. So it is not like that. Cosine similarity is more like if it even has the similar meaning, overall meaning, then they'll point in the same direction. If they are different, then they point in a different direction. That's cosine similarity. Another similarity which we call this as Jacquard similarity. So let's say that you have two group of friends, and if two people have a lot of friends in common, they have a higher similarity score. So but if they don't share many friends, then their similarity score is low and you will vibe less with them. So it's basically what it does. It focuses on comparing words directly. It measures the similarity between two sets of words by checking how many words are there in common. So let's say for questions like what is basketball, Jacquard similarity will match answers that include similar words like basketball, sport, or game. It fails to do something which has a different words but with the same meaning. So that's where Jacquard similarity is more like it's for finding matches when we want exact word overlap. So it's like it compares the two different words if the sets the two different set of words, and if the sets match with more words, then they are similar. If it does not, it does not. So they are not similar. So Jacquard similarity, but it fails to match different words. If let's say somebody says basketball, but might be a different name for a basketball, right? So they Jacquard similarity will fail to match it. Another one is Euclidean distance. So Euclidean distance is, let's say that you have two cities on a map. The shorter the distance between them, the closer they are, right? Similarly, two sentences close together in a space have more related meanings, just like in cosine similarity, but over here, instead of finding an angle between them, you find the distance between the straight line distance between the two vectors, right? Euclidean distance, all of this, I think you have already studied in mathematical part. It's pretty easy. So that's another measure of finding out the uh, what can you say? Finding out the similarity between two sentences or words. Over here, you're using embeddings, which are vectors which are plotted, and then you will see, okay, these are closely related, and then you use Euclidean or cosine similarity to figure out the exact score, right? So that is about the text similarity. Now, once you now I just wanted to clear text similarity in a very quick way. Now I want to cover something known as information retrieval. So let's say that
we have talked about how should computer focus on irrelevant words, how would computer focus on based on the context, how would computer figure out the scores of how similar two words are, but how would the computers or models will retrieve the information, right, will from the large pool of answers, right? So that's where it comes in something known as information retrieval. So let's say you are in a library with millions and millions of books and you want to find a book about space exploration. So what would you do if you are a non-guy, then non-expert guy? You will go ahead, you'll find every book and then see if it is a space exploration book or what. But if you use, but if there's an expert librarian, it will go ahead and then find out pretty easily, right? Or if you have information retrieval systems, find out those information very quickly, right? So I would like to take one example and I would like to talk about how this works and how this eventually works, how the information retrieval happens into three steps. So the first step is document representation. So what does document representation means? Document representation means that it converts the system, the set of sentences into a vectors, basically in an embeddings. So it eventually converts a vector into nothing but an embeddings or a set of vectors. That's it, right? So that computer can make sense out of it. That's what the document representation means. There are a lot of embeddings platforms. Some may be, let's say, one hot encoders. One hot encoder is non-semantic meaning. So let's leave that. Let's say word to vec embedding or other embedding techniques which we eventually use, which we'll learn a little bit later right now, what embeddings technique which we'll use to convert the words to the numbers. But first of all, you convert that turn text into a data. To search the information, an information retrieval system needs to represent each document in a way that makes the searching possible. If there's a string of words, it won't be possible. So you convert that text into numbers or vectors, which makes it easier to compare, sort, and rank information. Right. So it's like you are creating a catalog for library. You summarize each book by its genre, keywords, and main topics. Just that's why I say every chapter will have its own main idea. So use attention to find out the really important words, and then you convert that to an embedding, and that's your first chapter. That's how the document representation looks like. It basically captures text into numbers, which eventually the numbers should capture the key concepts and all. So there are different types of representation, TF-IDF, which we'll learn a little bit in a later part. Embeddings, as I'm talking about, it converts the words to a meaningful numbers, which tells about how closely they are together. And then the next step is a scoring and ranking. So representation, as you can see, that small dog, cute cat, cute is converted into you using bag of words. You've converted this into this particular vector. That's what the document representation means, so that computers can easily search. Another one is scoring and ranking, which is deciding what's the most relevant. So let's say you search for planets in our solar system. So the IR system scores document based on how closely they relate to this topic. So a document about Earth and Mars will have a higher score than about galaxy formations because it is more relevant. So use the text similarity scores to find out the like cosine similarity or probably Euclidean distance to find out the similarity scores and then rank them into a particular order based on the question. So it simply works. It calculates a similarity score using cosine similarity or Euclidean distance for each document compared to the query. So if the planets in our solar system, so it will compare to every document and we'll see which has the higher similarity score. Then you have something known as indexing. So indexing, so when let's say that you have a book, and into each book you have chapter number 1, chapter 2, chapter 3, chapter 4, chapter 5, and into this chapter you have several sub chapters and all. So indexing is just like that. It's a table of contents, so that let's say let's say you want to find information of photosynthesis. So you don't flip every page of the book, right? You go to the index, you find out the chapter where photosynthesis is discussed, and then you only search into that. So instead of going and matching the similarity scores in every document is assigned with some index.
And the solar system is talked in this particular chapter, and this is what. So eventually, indexing is nothing but it does the index to create a table of contents for the IR systems to find the documents very quickly instead of going through each and every document and measuring the similarity scores. That wastes a hell lot of time. So it's basically it creates a list of important words and links them to the relevant documents. And whenever a query comes in, it first of all sees the index, and then within the index, it finds the relevant documents, and then compares the similarity scores and gives you the relevant results. Right. So I want to take one example of Google search. So how does Google search works? So first of all, Google represents web pages by looking at the content, important words and keywords. So if you remember Google, you need to put, if you're from SEO, you put keywords so that Google would know that this article is about this particular thing. So whenever some question asked, they can eventually refer to those articles. And then Google assigns scores to each page on based how closely they match your search. So it ranks the pages based on the most relevant appear first, and then Google Index keeps track of which pages cover which topics, making the search more relevant. So if you have machine learning, data science content, AI content, tech content. So the indexing happens. So whenever the search comes in, it sees through the index and goes into that particular index which has the relevant document. And why I'm teaching all of this text similarity information retrieval, because in RAG, when we learn about, it's just about retrieval models and generative models, and that's it. So all of this really helps you to when you go ahead and understand RAG in much more in-depth level, because that's where you'll try to connect the dots of why we studied information retrieval, why we studied other details and all. So we have studied a lot of things. We have covered a lot of foundation, which eventually helps you to get a thorough understanding. Now, what we will do, we'll come to something known as uh, retrieval models. So right now you will come back to again information retrieval, because there are several ways how we can retrieve it. The process remains the same: representation, scoring, ranking, and indexing. Organize, locate, and rank. That is the way to think about this. So we'll eventually go ahead, learn about several retrieval models, because how do we represent the document? How do we score it? How do we rank it? How do we index it? So there are several ways to do it, right? Something known as traditional retrieval systems, dense retrieval systems. All of this we'll talk in great detail right now. And then we eventually go to generative models and then the RAG, and then we have the final project which we need to cover. I hope you're enjoying this. Let's catch up.
So now let's dive into retrieval models, which are like search engines within a system, within a models. So I want you to first of all let's imagine situation. So what is the full form of RAG? The full form of RAG is nothing but retrieval augmented generation. So what we will do, we'll break down the two components of RAG, which is retrieval and generative. So we'll talk both in greater detail. So into this particular module, we'll talk in detail about retrieving models. So they are nothing but like a search engine within your database or within your system. So to make you better understand what is retrieval models, let's first of all understand the need of retrieval models. Then only we'll try to frame a very nice definition out of it. So let's say that you are in a huge library with millions and millions of books, and you need information on ancient Egyptian history. Now, into the previous example, as I told you, why we need information retrieval, the same challenge was there. The same scenario I put there, that you're in a massive library, and if you're only expert only, then only you'll be able to pick out something. So it's the same way. The scenario is over here, that you're in a massive library with millions of books, and you have been asked to write a report on, let's say, ancient Egyptian report sort of thing, history. So instead of specific books on that topic, there are books on everything, because there are millions of books. So it ancient Rome, modern science, and even cookbooks or even other set of books. So the challenge is, how do you find the exact books that cover your ancient Egyptian history, and without even spending hours or even days sometimes flipping through each book and seeing where you'll find this particular information?
And that is where retrieval models comes into the play. That is where retrieval models plays a crucial role. So think of retrieval models as more like a highly trained librarians who understand exactly how to find the information you need, because it is organized in a particular way and your librarian knows about where you will find the particular book out there. And you ask for ancient to that librarian, and then he will be quickly pulling out all the relevant books from the shelves and giving it to you. So that is what the retrieval models helps to. It's basically retrieval models in RAG acts as these sort of librarians who search through a massive collection of a database and pinpointing you to the most relevant and pieces of information from the text. So if you search, I want to know about ancient Egyptian history, the retrieval model will know exactly where it is and will pull out the exact stuff and give it to you. That is what the retrieval models are. So if we go into the more definition architectures and all sort of thing, so it eventually helps you to locate the right information, providing the data to the generative model to answer questions correctly. So it's more like there are two parts of any system, of a RAG system: retrieval model and generative model. So whenever you ask a question like, I want to know more about Egyptian history, the in GPT also, if you use, first of all, retrieval models will retrieve the answer from the embeddings database, which we call this as a vector database, which we'll study. So it pulls out from the database of all the data, and then it gets that information, and then it gives to the another part, which is generative model, which we'll study in a bit. And that generative model will frame an answer and give it to you. So that is what the two-part system. So eventually it helps the generative model to locate the where the information is and eventually gives you an answer. So retrieval ensures that a generative model has the right information to generate useful answers. So if the retrieval is not there, it may not produce relevant information. It may not produce relevant answers or correct answers. So this is what retrieval models is in RAG. Now, there are several types of retrieval model. Two of the types which we'll talk about is traditional retrieval model and dense retrieval model. So each method, each type has its own way of locating information, and each works best in different situations. So let's say we will talk first about traditional retrieval models, which is something which we'll eventually talk about, and then we'll go ahead with dense retrieval model. So a traditional retrieval model is nothing but it's like a keyword search. So let's say that when you search for an ancient uh, Egyptian history, a traditional retrieval system will look out for documents such as. So let's say that you search for ancient Egyptian history. What this retrieval model will do? A retrieval model will find the documents which has the words like ancient Egyptian and history. So it only considers the document which has this exact keywords. So how the better way to understand this is, let's say that you search of something of benefits of exercise. So the retrieval models will go into all the documents, all the database, the data into the database, and then will only yield such documents which discusses advantages of physical activity, which means where the keywords benefits and exercise are there. Not entirely, sorry, this is the traditional model. So where that's why I was thinking, so it yields benefits of exercise, only those keywords which has this benefit and exercise. This is different one, sorry, by mistake I went to dense. But traditional, it's more about, if you search for a solar energy, it only retrieves those documents containing these exact words. So even if the document is related to solar energy, but the words are not present, it will not yield. So it's more like a term matching sort of thing. So it searches for exact keyword to match the query, similar to basic search engine which you will build. So let's say that as we took one example of let's say this ancient Egyptian history. So when you search for ancient Egyptian history, and the retrieval model will go through the entire database and only yield documents which contains ancient Egyptian history keywords. That's it. It will not produce anything which may be relevant, but if the words are not there, it will not give out. So that is what traditional retrieval models are. And The benefit of it is the traditional method is pretty fast and pretty simple because it's just term matching. So you just yield documents which are similar to that word, and then you get it all the exact stuff. So it works well when you need exact matches. That's it, because it only pulls out document where the exact words we are searching for. So the only limitation it has, that it is limited by exact words we use. So if we ask for solar energy, it may not find documents that use similar phrases like sun powered energy or renewable power from the sun. Even though the documents of renewable power from the sun or probably sun powered energy are similar to solar energy, but the keywords are not present into that particular document, it will not yield that such. So that is one of the limitations of traditional retrieval. It works well in many cases, but in real world scenario, it misses out the documents that are related in the meaning but uses different words. And that's another big challenge, that even if the document are related in the meaning but uses different words, that's where another challenge, and that's where this gives a birth to something known as dense retrieval models. So what does dense retrieval models is? So dense retrieval basically identifies meaning instead of the word and retrieve the information related concepts even with the different meaning. So it's like a instead of searching based on specific words, it looks for a meanings and concepts of that particular sentence. So if you search for benefits of exercise, it may yield documents even with advantages of physical activity instead of searching for exact words. So how does this does? So eventually it does this by turning text into embeddings, and then eventually the embeddings will have its own meanings and relationships. So whoever are closer to that, it will be yielding. So another usage of embeddings comes into play. So dense retrieval is more about embeddings and all those things. So, uh, dense retrieval is great for finding related ideas. It does not really rely on exact word matches. It can find information even which is relevant in the meaning, even if the wording is different. But the only down point is that is very complex, very slower than traditional retrieval models, because over here you literally need to find out the embedding and then find out the things which are more relate the embeddings which are closer to each other and then eventually suggest. So it requires a little bit of more computational expensive and more complex. So the role of retrievals in RAG is retrieval is essential for grounding responses with the relevant data to the generative model, so the generative model can produce relevant output. And traditional model, if you want to find exact facts and definitions, but dense retrieval is more for broader context and related ideas instead of just exact facts and definitions. So these are some exercise I want you to see. If you let's say that you have a search query known as how does exercise improve health? So traditional retrieval, what it will do, it will find direct mentions of exercise and health and then only pull out the information. But dense retrieval will find phrases like benefits of physical activity. It will yield such stuff. So I hope that it makes sense. These are few types of retrieval models and the why we really need and all those things. Now what we'll do, we will quickly go ahead and learn about each retrieval models in greater detail, which is traditional retrieval model and dense retrieval models. So now we'll go ahead and learn about traditional retrieval models. So there are two types which we'll study today, which is TF-IDF and BM25. And you will notice what problem we face in TF-IDF eventually builds up to something known as BM25. And these are very fundamentals. It may not be very in use when you actually learn it, but these are the fundamentals because they're building blocks of more advanced retrieval models. And you will notice the key pattern when you learn about RAG, you'll be easily able to understand stuff pretty easily, and you'll know the inner working of it, because most of the people don't know, and you will know the inner workings and everything. So let's start with retrieval models. I will not go into why retrieval models again. So I will just put you up with a scenario, right? And I want you to think about it. So let's say you are searching for articles on global warming from a vast collection. So the challenge is that not all articles focus on this particular topic. You'll have 100, 200, 1,000, 2,000 articles from different area, and not everyone might focus, but only few mention it very briefly. So retrieval models will score documents to help identify the most relevant one very quickly, as we have discussed the reason why we need retrieval models. But there is a way, but there's one type of traditional retrieval model. So in that particular scenario, how this retrieval model will work. So a retrieval model depends on keywords to match documents with search terms. So it's like it helps by giving each document a score based on how well it matches to your search term. So let's say you have 100 documents inside it, and you have something, and you search something with global warming. So retrieval, this the traditional retrieval model, what it will do, it will give the score of to the every document of how well it is matching to that search query, and the most highest the score, the more likely the document is relevant, and this helps you narrow down your search to the documents that truly focus on global warming. So maybe if you have received 5 highest scores, you just pull out the 5 highest scores and give it to you, but it matches the words, not the meaning. It matches the words global warming to all the documents out there. So one of the key things, these models heavily rely on keywords in a document that match your search terms, as I spoke. So let's start with something known as TF-IDF, term frequency inverse document frequency method, which scores, because I just told that that the search query and the document, so every document is compared with the search query and given a score. So how do we give the score? There is one way. So TF-IDF is a method that scores words based on their importance in an individual documents and across all documents in the collection. So let's start by what exactly the goal is, what exactly the TF-IDF stands for. So TF-IDF is nothing but term frequency inverse document frequency, and there's two parts of it. The first part is term frequency, which tells you the importance of that particular word into an individual document, and IDF, it measures across all documents. So the first one is TF-IDF. So let's talk about term frequency in greater detail, and then we'll come to the definition and all. That in the term frequency, I want you to take one example. So an example says that in an article about global warming, the word warming might appear 10 times. So you have an article which is about global warming, and global warming appears around 10 times. So this will be having a higher term frequency score because the term into that particular document is about 10 times. So you'll get a higher term frequency out there. So it's more like that words that appear more often into that particular document. So let's say that you have a document which is just telling about climate. So that document is about climate change. So if an article is mentioning about global warming 10 times, that article is about, the document is about global warming. So it's more like words that appear more often in a document are more likely to be important on the document's topic. So it's nothing, but it measures the frequency of a word within a document. So when you search for a global warming, or when you search for global warming, it will search into every document. First of all, every document will have its own heading sort of thing, that I'm about this, I'm about this sort of thing. And inverse document frequency, what it does, common words like the and all those things will have a lower scores, while specific terms like greenhouse are higher. So to understand this much more better, so let's say that uh, uh, you have in a document, you have something known as the and a, I, and all those such keywords. So what IDF does, IDF lowers the importance of a common words. So if there's too much of common words, it lowers the importance of a common word. But greenhouse is little rare word, so it will give a higher score to something which is greenhouse in this case. So basically it gives the higher score to the rare and topic specific words instead of common words. So even if the appears at 100 times, it will give a very low score. That's for the inverse document frequency. So inverse document frequency measures how rare or common a word is across all documents. If it is rare, it gives a higher score. If it is common, it gives a lower score. So I want you to walk through an example. So the TF-IDF formula is TF multiplied by IDF. That's it. And you'll get a TF-IDF. So TF for warming. So let's say the word warming appears 10 times in a document of 100 words. So you have a document and the warming appears 10 times in a document and the document has 100 words. So the TF score would be 0.1. Now, if warming appears only in 5 out of 100 documents, its IDF score will be high. So TF is for individual documents and IDF is for across all the documents, how rare or how common this topic is. So let's say that warming only appears 5 out of 100 documents. So you'll eventually yield around 3, which is the IDF score. And then you multiply TF multiplied by IDF, you get 0.3 as your TF IDF score. So that is the score which you'll get when you search for global warming. That document will get this particular 0.3, right? So then the TF-IDF score will be calculated for another document. So if that document has zero warming and zero mentions of warming, and the warming as mentioned is again the IDF would be also zero, so it is zero. Right, so document number 3 again. So you calculate TF-IDF for every documents out there, and then the scores, and then you see which has the higher scores. So to understand this very simply, very simply, that let's say that if a student searches for global warming documents with high TF scores, TF-IDF scores for words like warming, emissions, greenhouse are likely to be more relevant, right? So it's basically gives you the scores to each document by calculating the search. So if your search is global warming, it will calculates that search query, and then it calculates the TF-IDF score for each document. And then let's say if you have another query known as climate change. So climate change. Okay, I go to the first document, I go to the second document, I go to the third, fourth, fifth, sixth, all the way down to the end, whatever the documents which you have right now, and then you see from it, and then you eventually produce. So TF, IDF, but this only happens via the words, because over here you're counting the number of mentions in the particular document and number of mentions across all the document, right? So that's what the TF-IDF is. It's pretty simple, pretty easy to understand, and I want you to, if it is very simple, you just need to recap if you're having a hard time to understand it. So now we come to something known as BM25. So BM25 is an advanced retrieval model. So it's basically a smarter version of TF-IDF. So it improves on TF-IDF on two important factors. The first factor is frequency saturation. Saturation. And second one is document length normalization. So let's study about these two things in a greater detail. Now, in the frequency saturation, a word that appears more time into a document does increase its relevance. If a document is having warming 10 times, then it might be a warming document. But let's say that warming appears 5 times is important, but appearing 50 times does not make it more relevant. So what it really does, let's say that you search for a particular parameter, warming 5, it appears 5 times. But if it appears 50 times, does not make it will consider, okay, now the warming is important. But if that is mentioned 50 times, it will not consider that, right? It will say, yeah, I know you are capable of doing it. So it's like basically, I know you're capable. You don't need to prove me. Even if you prove me, it will not help me out. So BM25 captures this by saturating the score for the frequent terms. So it saturates. So if the warming has been mentioned 5 times, be at 5, because being at 50 will not increase your, it will not make you 10 times more important. So it saturates, it gives you the saturation that you should stay at this. That's it. Because even if you go beyond this, I'll be not able to help it. It's just a computational expensive sort of thing. Then another one is document length normalization. So what does it really mean? Long documents tend to have more words in general. So let's say that you have 10 longer documents and 10 shorter documents. 10 long way which has thousands of words, and shorter documents will have us a few hundred words. So to make sure that we are not forgetting the shorter documents, just by looking at the longer documents with the more words, to what you can say, normalize this situation, that we, just like in machine learning, you have something concept known as overfitting. The same way over here you have document length normalization. So it normalizes the length so that every document receives its importance. That's it. So it actually focuses on two major problems which it solves, which is frequency saturation. That if warming appears 5 times Okay, I know you're important, but appearing 50 times into a document does not makes it 10 times more important or relevant. So it eventually saturates it so that the numbers do not be biased. That's another one. Okay, so it does this by two important parameters, which is K1, which we call this as a term frequency saturation, and another one is document length normalization. Now, what is K1? So K1 controls the impact of frequency, and B, which is the document length normalization, as I said, it adjusts for the document length to avoid any biases, so that even the shorter documents are being looked after. So parameter K1, it controls how much score increases with frequency. That's one. So if a word appears very frequently, K1 prevents it from unfairly boosting the document's relevance score. Right. So let's say that if you have into TF, a document contains 100 words out of 100. I mean, all the 100 words are warming, right? So it will give you direct one, right? Direct one. Now, IDF only three times appeared. Sorry, five times. So you'll get three. So one multiplied by, so it's three, which yields a very high, um, what could three, which is a very high TF IDF score. But just writing warming does not help, right? So to make sure the relevance is still there, to make sure that it's not unfairly boosting up the document's relevance score, this is a parameter to control it. The B is it controls how much document lengths impact the score. So it eventually prevents the documents from being too scored too high because this contains more words. So it basically normalizes both number of times the word has been taken name, and secondly how long, so that the shorter documents does not gets ignored. So I want to take one example, which is for queries. Let's suppose you are searching for effects of greenhouse gases. So with BM25, I forgot to tell you the full form of it. BM25 is nothing but best matching 25. Okay, so suppose we are searching for effects of greenhouse gases. So with this algorithm, with this retrieval model, documents that focus more on greenhouse gases in depth, which is where I'm talking about in depth, not just the words, it will be ranked higher even if they're longer, because even if they're shorter. So that's where TF-IDF improves. So what is the key difference between TF-IDF and BM25? TF-IDF might give, let's say that you search for a warming. So TF-IDF might give all the documents similar scores even if they contain the keyword known as warming. But BM25 would rank documents with more balanced approach, prioritizing relevance based on not the sheer length or number of times it has been appeared. That may go very biased. So this is the basic difference between both of it, and I hope that it helps you to understand the TF-IDF and BM25, which is a more retrieval, and you can see how BM25 eventually builds upon TF-IDF to be more relevant. Now, one of the key thing which I want to mention is you will see that when we study about dense retrieval model, you will see that how well this particular model improves on top of it. So BM25 has its own limitation. So it's still doing based on the words, but it's trying to extend it by stating that I'll give you little more relevant than what TF-IDF can give. So the same way dense retrieval will say, hey, listen, I'll give you the best relevant stuff. So let's talk about dense retrieval models in a greater detail now. So now I'll go ahead and talk about something known as dense retrieval models, where we go beyond keywords to understand meaning. I think that this is my favorite topic whenever I teach into the classes too. It's something which eventually I also love to teach, because when I first of all, so I saw when I was learning RAG, I was seeing a lot of tutorials on YouTube, I was seeing a lot of blogs, and nobody was really telling me what is the inner working behind RAGs when we actually use it. And this is the inner working behind it. This is something which eventually goes ahead. So I want you to Because I always believe in a scenario. I always believe in something which I could present to my students and then eventually get it. Why do we really need it? So I want you to think about a problem. So let's say that you're studying for a science quiz and you want to learn about ways to stay healthy. It's that. And you start by searching for articles or notes on this topic. So some documents may contain ways to stay healthy. Exactly. So ways to stay healthy, let's say like that. While other phrases tips for a healthy lifestyle or steps to improve well-being. Although these phrases means the exact same thing, but they don't really contain the exact words. Traditional retrieval models will fail to answer this because the words and the documents are very different. The phrases are very different. So even if you search on a Google, you'll find several documents which are relevant but not match the exact. But it matches the topics based on the exact words, but it finds the more relevant words even if the meanings are not same. So traditional model, as I said, will only find documents that match the exact words, which is ways to stay healthy. But dense retrieval models are different. They look for a related meanings and can recognize that healthy lifestyle or improving well-being are also relevant. So that is the challenge is that it is hard if you search ways to stay healthy for a traditional retrieval, it is hard to find out these challenges. But the solution is that you have something known as dense retrieval models, which is they look for a related meanings and can recognize it. So it's like it's an ability to understand the meaning and how it comes from embeddings, because embeddings are nothing but a vector with relationships. So a word converted into vectors with relationships. So it's like a code that captures the core ideas. The embeddings are nothing but the code that captures the core ideas behind words and phrases. Right. So there is something known as uh, I'll just go ahead. Yeah, something known as DPR, which is dense passage retrieval. So DPR is a dense retrieval model because in traditional we had something known as TF-IDF and BM25, and DPR is one of the model for the dense retrieval and which we'll study throughout. So DPR is a dense retrieval model which is designed to find information based on the meaning because it's the same. It basically tries to find meaning instead of just relying on exact word matches. So how DPR works. So DPR is used currently in huge systems, which is QA, question answering systems, search engines, even Google and all these big giants use dense passage retrieval to in such applications and all. And um, it's basically that when you search for healthy lifestyle, that is represented as embeddings, like a vectors of words. And then you have several documents which are also represented as embeddings. And then what happens that the questions are then compared with using similarity like cosine similarity or Euclidean distance. You get the score that question's embedding is then scored with. This question embedding is then scored with every uh, embeddings of the document, and then which whoever has the highest score are being recommended. It's as simple as that. You don't really need to worry about. So I will not go in buy again use because we have talked about a lot in detail, and I want to talk about it's how it works and what is the inner working of DPRs and all. So DPR creates embeddings for both queries and passages and documents, which is so if you ask a sort of question about benefits of exercise, the embeddings are created for this question, and then you have several documents which has its own embeddings. So what it does, it finds the most similar embeddings for the retrieval based on the question asked. So how it does, it compares the embeddings. It compares the embeddings. So basically, it compares the embeddings and it identifies the documents which is close to the meaning in the query. So what are embeddings? That is the I want to again go back and tell you a little bit about what are embeddings. Embeddings are nothing but a dense of vectors or a set of numbers which represent the meaning of the text, which represent the meaning of the word. So let's say that uh, you ask a question about benefits of exercise, and a document talks about positive effects of physical activity. But benefits of exercise is not, I mean, the words may be different from the document, but it has the same meaning. So embedding for these phrases will be closer to each other because they share a similar meaning. So that's what the embeddings, because it is very, very important for us to embeddings are very important because it helps the dense model to understand and retrieve conceptually related information, not word based or meaning or word exact word matches sort of thing. So eventually, the DPR uses something known as dual encoder architecture. So, what is dual encoder architecture? So, as I told, DPR creates embeddings for both, one for the query and one for the documents. So, there is two encoders, which is one encoder for the question and one encoder for the passages. So each encoder transforms the text. As I told, the encoder you can use any encoder. There are several types of encoders. So if you ask a question, then that is passed from an encoder, and that creates an embedding. Another encoder passes the passages, pass the passage from the another, and that creates another embeddings. So why we do not use a single encoder to encode both of them? It's because if using two encoders, it allows this model to treat questions and documents differently. And then you can go ahead and compare it. And then you can go ahead and compare it out there. So we give a different name. The query encoder creates an embedding for the search question, and the passages encoder creates embedding for all the documents. And then it compares the embeddings to find the documents that closest to the question's meaning out there. So let's say that you have a query of let's say that you have a query of how does physical activity benefit health. So the query encoder will turn this into an embedding first, and then the passage encoder will have embeddings for all the possible documents, and the DPR will identify the document that best matches this question by comparing embeddings. So how how this algorithm, this dual architecture is trained so that it gives the right answers. It gives you the relevant information. So to train a DPR, the model learns from both positive examples and negative examples. We can also call this model learns from the examples of relevant and irrelevant document query or document pairs. Right. So let's say that you have a positive examples. So when in the training process of DPR, because DPR has to be trained, in the positive examples, queries and documents that match, like what are the benefits of an exercise with the document about exercise benefits. So basically, it's like you give a good positive examples and then you give the negative examples. So positive examples where the matching is correct, where the question and the matching of document is correct, and negative example where the matching and the non-matching, there's a non-matching of if the question is one and the documents which are suggested were not correct. So you use both positive and negative examples to train your DPR, which is as simple as that. So positive examples helps DPR learn what a good match looks like, while negative examples teach it what is not relevant. So it's basically just like a human do. You see positive and negative and you know what to do, what not to do. And this way, DPR learns to recognize relevant documents and ignore irrelevant documents because it has been trained on both. There's no in something in middle. It's as simple as that. So as I told, the how does DPR learn relevance is basically matches in positive reinforcement. It matches the pair, strengthen the connection between relevant, and non-matching pairs reduces connections between unrelated. And then this refines the DPR's model's ability to find and prioritize relevant information accurately. So I hope it makes sense. And I hope that you got the point of I have not went into DPR of encoders architecture where you encode the words into a document and decoder is where what the output comes in and then you eventually frame. We'll talk about decoders a lot into generative because currently we're just talking about encoding. So encoding is nothing but retrievals because you need to encode the words into the embeddings and that embedding has to be so dense retrieval is nothing but If you search for something, you create an embedding and you have the embeddings for all the possible documents, and then you truly match which is correct. And the training happens by giving positive and negative examples to the model so that model knows how to find and prioritize relevant information accurately. So I hope it makes sense. I hope dense retrieval model makes sense. And that's it about dense retrieval models and all those things. Now what we'll do, we'll talk a little bit about vector databases, and then we'll eventually go to, we'll use something known as PG vector scale, because there are a lot of vector databases. We'll talk about vector database in great detail. And then we eventually jump to something known as generative models, which will give you a more broad understanding of how, even though you find the documents, now what? Now, after finding documents, now what? That's where the generative model comes into play, which will help you to, um, which is known as decoder into this case, where we eventually go ahead and find the stuff. So I hope it makes sense. Let's go back and let's go ahead and learn about vector databases and generative models.
So, hey everyone, now we will go ahead and talk about something about generative models. And generative model is another building block of your whole RAG structure. So into the last couple of modules, we eventually talked a lot about retrieval models, how it retrieves using embeddings and all those things. So now it's the time for the generative model. And to better understand about generative models, let's first of all look at the limitations of retrieval models and what is the problem which came, which eventually generated something known as generative model out there, and how generative model overcomes the limitations of retrieval models. So to talk about it, retrieval model is nothing but it helps you to scan the documents, and whenever you search for the query, it gives you the relevant information. That's it. It gives you those documents or those kind of a sentences which matches with your query. So if you ask for what is photosynthesis, it will take that photosynthesis and start matching with your documents, and will pull out those information which has the word photosynthesis in traditional retrieval systems. And now to better understand, like what is the big problem which comes into the play, let's say that when you search for, let's say, photosynthesis process, so you get all the pieces of information that have the words photosynthesis and process. What really comes out as an output from the retrieval models are nothing but a list of sentences or phrases that contains the right words. But let's say that you have those documents which contain some words. Let's say you have three documents. The model gives you the three documents, the three sentences. First sentence, please hear me carefully, is photosynthesis is a process used by the plants, right, to make food. Another sentence which eventually retrieval model sends out, that it involves sunlight, carbon dioxide and water. And third sentence is the plant produces glucose and oxygen as an result. Now let's say that somebody asks a question about, tell me about photosynthesis process. It has these valuable information. It retrieves these three sentences, which is very valuable. But it is not clearly communicating the response. It is not clear in response. It should be very smooth. It should be it should contain a one shot full answer, which the way, like if somebody asks you what is photosynthesis in the process, you shouldn't be telling these unstructured information by three lines, right? You should be very clear, coherent and smooth response instead of three blunt lines. So the actual problem which comes with the retrieval models is you get a list of words, sentences, or phrases which contains the right information, but not in a way that can be given out to the user, which is more clear, more crisp, and clear response and smooth response out there. So that's where the generative model comes into the play. I want to think of one more example out here. So let's say, imagine your teacher gave you several pieces of information on photosynthesis from different sources and asked you to create a paragraph explaining it. So what you will do, you will take all these information and then eventually you will use your understanding in English, and then will try to write in a way, you pick the important parts from it and write in a way that flows, that you may start with photosynthesis is a process that is used by plants to make food, which involves sunlight, carbon and dioxide, which helps plants to produce glucose and oxygen as a result. This will be your answer when you're given several sources, right? You do not just pick out those sources and push it there. You'll be making a very crisp and you'll create a paragraph explaining it. But retrieval models can only give the information. So that's where the foundation of generative models starts in, and that's where the formation of generative model starts, which helps you to make information clear and complete. So you can see in the slide that the issue with the retrieval models, which can retrieve the relevant sentences, but they often lack coherence with piece together, which means float together, combined together in a way that makes a complete answer. So users typically want a complete, understandable answer without the need to reorganize the information and then get it from their own. So, how does generative model goes ahead and create? So what is generative models into this case? So generative models generates the new sentences by predicting one word at a time based on the words that comes before. Now that is the one of the thing which might confuse you. So let's understand in this way. That it predicts the next word. So if say photosynthesis is the process by which plants use sunlight, and then the generative will predict the next word, which is carbon dioxide, based on the previous word which came before. So that if somebody says sunlight, then the next one should be carbon dioxide, because it says that photosynthesis is the process by which plants use sunlight. So the next word is being predicted by looking at the previous word, which is sunlight, process, then carbon dioxide, and then the water, which is again looked by how photosynthesis is created. So so generative models generates new sentences by predicting one word at a time based on the words that comes before, so that it makes a complete answer, coherent answer, and very smooth, because it will know, okay, this came at this because previous word is this, then the next one should be this. So you can think of them as a talented writers who takes different set of pieces of information and then it turns them into a story, into an understandable answer, right? So that is the generative models are. Right. So into the slide which you can see, the purpose for them is to build sentences word by word for natural coherent answers by taking in the information from retrieval models. And think of them as like a talented writer which takes the information and then potentially creates it. So what is the process? So models predict each word sequentially, creating a smooth and logical sentence. So if it says photosynthesis is the process, then it predicts the next word. Okay, it should be sunlight, carbon dioxide, and water, because it has been talking about photosynthesis process. So to make it very smooth, to make it very clear, they actually predict the next word sequentially in order for it to make it logical and smooth. So the next step is how it helps to solve the challenge. How it helps to solve the challenge of these three things. The first one is coherence. So the coherence, there are three main ways where generative models helps in solving this particular challenge of non-coherent and non-complete and non-adaptability answer. Is they connect the pieces of information into for easy understanding, full flowing sentences. So that's the first ways where generative model helps. It connects the information in a way that is easy to understand, that makes your answer easy to understand into full and flowing sentences. Another one is completeness. They build a response that includes all the necessary details without needing you to piece together separate sentences. So you get a complete answer without any gaps inside it. Another one is adaptability, which is they can answer questions on different topics or in different styles. For instance, let's say if you ask about, can you explain photosynthesis in simplest term? So instead of the retrieval model will give you several responses, which may not be in the simplest form, but generative model has been asked to make it in the simplest form. So it will make that into a simplest form instead of using hard and harsh language or jargons out here. Right. So that's why if you search on it, just try to search, explain me generative model like a class 5th student. So it will help you to tell you in a class like a class 5th student. Now, if you tell to explain generative model like my PhD student, it will explain you like a PhD student. So you will see the retrieved information will be same, but the way it makes adapts to your question, that is what makes a generative model so powerful. So how generative models work? And there are several generative models. The first is generative, which is GPT. And then we have T5, and then we have BART, and then we have so many generative models out here, which helps you to frame those level of answers, adapt it, and then have the completeness and coherence in their answer. So how does it work? I'm not going to go too much in mathematical details, but I want you to know how it exactly works whenever you use GPT and all. You will know that uses generative models uses attention mechanisms to focus on the most relevant parts of the retrieved information. So that's the first step. That let's say that somebody asks for photosynthesis. So it uses that attention mechanism to focus on the important words only and ignoring irrelevant details. So if the model sees the word photosynthesis, it might pay more attention to related terms like plants, sunlight, glucose when generating the next. So it uses the attention mechanism to focus on the most relevant thing and relevant terms to maintain the relevance out there. And then it predicts the next word. So once the model knows what question is about, it predicts one word at a time to form a sentences to make it coherent and cohesive and probably and adapt to the tone. It's like you write a story building on each word to create meaningful sentences. So if you were told to write about tell me about photosynthesis, it will tell you, it predicts the first word, then second, third, fourth, fifth, to make it a continuous flow from the retrieved information. And then you have decoding the response, which is the model keeps predicting words until it completes a sentence or a paragraph that fully answers the question. So it keeps on predicting the next word unless the model feels like, okay, I'm done. And this is something which we call as decoding. This is what we call as decoding, where it generates a complete coherent response by adding words one by one. So the way generative models work is uses attention to focus on the important details and important terms from the retrieved information, and then uses the model to generate one word at a time based on the question, and then it keeps on generating unless there is a full stop or completeness of your answer. I hope it makes sense. Now, I want to talk about a very quick detail on the difference between retrieved models and generative models. So, in retrieval models, it finds an existing information. But in generative models, it creates new sentences to explain the information. So you might find several information, but you need to explain it. You can use Google to also find such information. But generative models eventually create new sentences using those retrieved information. They are often disjointed. They are like a list of information, but generative model are like smooth, connected, and it flows naturally out there, and it delivers full and clear answers on that sense. So I hope it makes sense about generative models. Now what we will do, we'll walk through a simple example where we'll combine both retrieved models and generative models, and then we'll try to build a system on top of it. So now let's go. If you haven't understood into this lecture, don't worry. In the next one, you will see example which will help you to understand it much more better. Now, I want you to see this example, which is pretty important. So the example will include both retrieval and generative step. So whenever a question is asked, the model goes through the first phase, which is the retrieval phase, to find relevant content in a large database of text. So the first step is transforming the question. So whenever the question comes in, it transforms that question into a vector. So let's say somebody asks, how does photosynthesis works, which is represented in a vector with embeddings. So it is because the question has been converted into embeddings. And then the question, when it is converted into embeddings, we use a vector database. So we have already talked about it. We'll use a pgvector. So this is a database which stores the vectors that represent the key information on different topics, such as photosynthesis, climate change, and all those things. So you'll be having this vector database which will have all the information on different set of topics. And now I will not get into detail of vector databases right now because we have already explained it a lot, and we'll talk a lot about once we do the project. But this database will have a lot of information, not only about photosynthesis, but about climate change, water cycle, and all these things, and in a very relevant format, which makes it easy to locate. Now, this question about how does photosynthesis work, if you're using a traditional retrieval systems, it takes this photosynthesis words and try to match with all the stored vectors using similarity measures. It might use cosine, it might use Euclidean distance to find the closest matches. So the first step is that the model retrieves for example, somebody asked for a question on photosynthesis, there might be several retrieved phrases which may include plants make food, involve sunlight and carbon dioxide, and several other chunks of information. So the next step is, once you actually have all this data stored in a vector database and your question is being converted into embeddings, you find similar vectors which is into the database, which means the vector representation of the question is then compared to the vectors stored in the database using a similarity measure. Now, once you do this third step, similarity matching, you will get a bunch of retrieved information. You'll get a bunch of retrieved information, which will tell you the most relevant information based on the similarity scores, right? So it picks out the most relevant information out there. For example, for a question photosynthesis, the results might include process plants used to make food, involve sunlight, CO2, and water. So these are the retrieved information once you compare the question in vector embeddings with all the photosynthesis with all the documents if you're using traditional, and then you take out the top similarity scores, whoever documents had got the top similarity scores, and these two sentences has got the top similarity scores. So this step narrows down the vast amount of data to just the information that is most likely to help answer the question which was asked, which was about, tell me about photosynthesis. Now, once you have this retrieved information, then the generative models comes into the play, and generative model takes over a task like a GPT or probably some T5 or some other generative model, which creates a well and cleared and structured response. The first step is it understands the retrieved information. So the generative model receives the question and the retrieved content as a context so that it reads through this content to understand what points have been provided. So basically, first of all, it understands. So whenever you get a fact, and if you're to make this fact to a paragraph and a flowing sentences, you will first of all understand the full context of it and understand the key points. And then the next step is generate a coherent answer using attention mechanism. So this model uses attention mechanism, which means focusing on important words within the retrieved information. So these two information which are retrieved, it focuses on those important it uses the attention mechanism to focus on important words, which is into this case photosynthesis, sunlight, and glucose, which pays more attention to these words to maintain the coherence of it. And then in step 3, it predicts each word in the response one at a time. So once it starts generating a response, it predicts what should be here and the next one based on the previous one, step by step, which means this process is known as decoding. Now, let's say that somebody says, I will take one example. So let's say that photosynthesis let's give an example. So photosynthesis, the first generative is photosynthesis is the process by which plants ... So the model will predict use sunlight as the next words because that's what the next word should be, because it has been seen, okay, I should predict this word based on my previous context. So the photosynthesis in which process by which plants ... which means now it predicts use sunlight, and then it predicts carbon dioxide, and then it predicts glucose, and so it will continue like that in order to make a full and complete sentence. So it will keep on predicting unless your decoding process is done. So to tell you about the 3 main mechanisms, which is attention mechanism to focus on the retrieved information to build relevance in the answer, and predicts and keeps on predicting the word based on the context, forming the full sentence, and it continues predicting until the full response is generated. So I hope it makes sense. Now I want to talk about these. I will just summarize all these retrievals and generation into 2 steps. So whenever somebody asks a question about how does photosynthesis work, the retrieval models comes into the play, which converts the question into a vector And then it searches the vector database for a vector similar to the question, which means it compares the question vector with all the vectors into the vector database to find which is similar to the question, and then it retrieves the relevant information by using similarity scores. Now, once you have the relevant information, it goes to the generation step, which means the generative model reads the retrieved content to fully understand it, and then it uses attention mechanism to focus on what's really important to ensure accuracy, and then it predicts the words sequentially, which generates the answer one word at a time based on the retrieved facts, and then it keeps on predicting like a decoding process unless your sentence is complete. And this makes a full RAG structure and an architecture. Now, if somebody, I have seen so many people just jumping into RAG explaining what it is, but now I went through a lot of problems that this was the problem and this was invented. This was the problem, this was invented. Now I hope that is very clear why we studied information retrieval, why we studied embeddings, why we studied vector database, why we studied retrievals and all those things. So I hope it really makes sense. Now what we will do, we will talk a little bit more about retrieval models. We'll talk a little bit more about RAG, which is RAG architecture. Technically, you know everything about RAG theoretically, which you need to know. But now we will go a little bit more deeper in understanding why they are so effective. How exactly, what are the benefits of it? Why do we really need it? To make sure, because we'll be studying the same thing again, but I'll make sure that I give you the formal definitions and probably formal understanding of what RAG is. I hope it makes sense. We'll complete RAG very quickly and then we'll jump to our very first project and one of the most advanced project of LexiChat. So I hope it excites you. Let's focus us on the next one. Now we'll go ahead and talk about something known as RAG architecture, and it's nothing but combining both retrieval and generative models in order to make this RAG architectures, and that's why the name is retrieval, which when we augment it, that gives a part to the generative model. So that's where the name comes from, that if we augment retrieval model, we eventually get something known as generative model. So the RAG architecture, it's an approach to combining these two types of AI models, which is retrieval models and generative models. So this combinations allows AI and gives a powerful technique for them to answer questions, explain topics, or summarize information in a way that can be both accurate and easy to understand. Accurate by retrieval models and easy to understand by generative models. So we have been doing too much of theory, and I want to take a last one for theory, and then we will eventually go in too much of practicals, because that's what the practical is very important for this. But I want to take a time to tell you again what retrieval models and how exactly the whole RAG architecture and why there's a need of it. So let's say, why do we need to combine? That's the first question which should come. And now at this point of time, I don't need to tell you why. So I hope that you got this answer of why we really need to combine. So let's say that you're preparing for a science quiz and you want to study about photosynthesis. But instead of flipping every page through your book, you prefer to get a clear and direct answer, right? So for that, you will search Google and you'll go ahead and then you first of all find an accurate information from the trusted sources. And then you should use those sources to explain it clearly. And that's what both the retrieval and generative models helps you to do. So the capabilities of retrieval models will be to find the relevant information from a database or a collection of documents. But the only problem with them is they struggle to make responses which are more coherent, which are more complete, which are more adaptable towards the question, because they'll give you the list of ideas, list of phrases, list of sentences. Then the generative model will take all of these sentences and eventually get all the context and then prepare a full grounded sentence, which is craft a fully connected sentences. Now, if you do not give the retrieved information from the retrieval model to this, it may be not good enough. It may lack accuracy. So accuracy is defined by how well the information has been extracted, and generative models helps you to use those extracted information to make a well-crafted answer. Now, what is the benefits of combining both? Why do we really combine it? First is a factual accuracy.
First is the factual accuracy, that the retrieval models gives you the correct answers from the trusted sources, the grounding, the responses. Basically, it gives you the accurate information from the trusted sources. And then the generative model will organize the facts into a smooth and readable answer and adapting it to the mode of question, and then together combining both of it will deliver responses that are both correct and easy to understand. That's what gives then art to or delivering to RAG, retrieval augmented generative system. So as I told that there are two systems right now, which is the retrieval model and then the generative model, which both combines to make factually information correct and articulates smoothly. Now, how? So if you mention the word is retrieval augmented generative systems. Now, why there's a word of augment? This is the reason. So without retrieval, a generative model alone may guess answers based on the prior training. So the training might be very outdated of GPT models and all. So you need something which is so let's say that if you go and ask to GPT about what happened. So you're having several chats, right? And then the model might not be trained on it, right? So it may guess the answer. But if you already provide, hey, listen, this is the database I have from where you should pick my answer, that's where the retrieving things happens. Because if you want to make something known as, let's say, second maybe chatbot sort of thing, so you need to know what chat has already been done in order to provide the next. But GPT is not trained on those chats, right? So you tell, okay, these are my chats, you should retrieve the information from these chats and then only give me the information. So without retrieval, it may only guess, but training does not happen real time. It happens it happens based on the prior training, so it may not be able to guess answers correctly. But the generative model with retrieval, it will have the specific and the relevant information to use, which eventually increases its accuracy in its responses. And what is the augmentation effect? The augmentation effect is nothing but it grounds the retrieval step, grounds the generative model, making the final answer both correct and clear. That's why the word augments are there. Now I want to take one example. What are the effects of global morphing? So retrieval model will give these phrases, and generative model will use all the three steps: attention mechanism, and then forming the coherent sentences, and like predicting the one word at a time, and the decoding process to give this final response based on these sentences. Now, what is the workflow of RAG pipeline in action, which we'll also implement once we go to the designing of LexiChat? We'll eventually go through this. But what is the workflow of a simple pipeline? First of all, let's say a user inputs what happens during photosynthesis. The system converts the question into a vector to identify similar ideas, and then it compares those vectors from the vectors which is already present, which you are given into the database. So you should take the information from there, compare it from those relevant information, and gets the topmost similar scores. Now it feeds the information to the generative model. So whatever information is retrieved, it feeds to the generative model to know about the context along with the question. And then the generative model uses those retrieved data and questions to create a clear and a complete answer. And then it eventually outputs, which is easy to understand. And this is the combined RAG system. So I hope it really makes sense about RAG and how it eventually helps combining both of it. And I hope that you know the essence of the meaning of augmentation. Now, from now on, what we will do, we'll focus on the practical aspects of implementing it. We'll talk about pgvector, and then we'll talk about vector databases, and then eventually we'll work on to our final module, which is our project, which will eventually help you to learn more about it. Looking forward to chat.
Hey everyone, now we come to our first basic project where we're going to implement an interactive Q&A system using retrieval augmented generation. This is a very basic process. I want you to understand the essence of what step-by-step in RAG looks like, so that when we go to the LexiChat and we build that agentic system where it chats with a document with taking entire context, you'll be easily able to understand that major project. So before coming to that, I wanted to ensure that you already know some of the parts of it, some of the processes to it, and the whole pipeline,
of how does the RAG looks like in action, but still you have some way a very nice understanding of how Q&A systems are built. So this is an interactive Q&A systems where you ask a question and based on the information, it yields you the answer. So it's like you give them a bunch of information, bunch of documents, and then based on those documents, it will, if you ask the question, it will answer based on those documents. So the very first step which I want to talk about is how this Q&A system will look like. So what we will do, we will have a set of text, a sample text, because I have not taken it very often. So what I'll do, I will simply take a bunch of texts, and that will be acting as our knowledge base. And then step one would be the document chunking. So if you have a PDF, so if you remember or recall our conversation was you convert that text or a sentence into words or maybe phrases of words or maybe chunks, right? For the computers or models to understand it well. The same way we convert a bunch of text into chunks. I've already did that to you, but when we go to the real world system and somebody uploads a PDF, the step one comes in converting those PDFs into manageable and understandable chunks so that can be given to the models to understand it better instead of just giving them the whole bunch of text. So that's the step one. Then what we will do, then we will go ahead, because the next step is once the chunks are generated, but still computers cannot really understand from those chunks, it has to be converted into embeddings. And there are 3 chunks into this project, and this chunk has been converted into several embeddings. So each chunk has been converted into embeddings of 1536 dimensions. Previously, it was very small, but now there are 1536 dimensions. What does it really mean? So this text has been converted into a vector that has a 1536 dimension, which means that it yields 1536 ways of representing this text. Yes, you heard it me right. So if you remember machine learning, and in machine learning you have a data in which you have 13 features, 14 independent variables, and these are 14 dimensions. They are dimensions, right? 14 dimensions. So every feature represents something. The same way, every dimensions represents something into this chunks, and this embedding will be generated by one of the best embedding model from OpenAI. And this has not to be trained from your side. It's just that it is already available. So you'll make use of already been available embedding. We'll not go into integrity details of how these embeddings and all those things are trained. They have a separate training process that has to be learned. So basically into this, it has around 1536 dimensions, in which every dimensions represents some part or a relationship between these words, right? That's the first. Same goes for the next chunk, same goes for the third chunk. And once we have the embeddings retrieved, then what we do, then we ask a question. Let's say I ask, what is ML? And then what it will do, it will convert this question into an embedding, because if you remember our conversation, our discussion, it was around, then we convert the retrieval process is done. Retrieval process is chunking and generating embeddings. And then if the question comes in, then what it does, it uses that embedding and the embedding of the question, and then it uses the similarity search to find out the relevant context or chunks for this question. And then you get the relevant chunks. However, over here, there are 3 chunks because I've continuously run there are 3 same chunks because I've continuously run the same database. So it yields the 3 stuff from there. So they are all same, right? Now, once the relevant chunks are generated, now there's a part of the generative model where it uses the OpenAI model itself, OpenAI generative model, to use this accepted or to use this relevant chunks in order to make the cohesive and concise answer. So it says based on the information provided is a subset of AI that enables, and this is from here only, but it makes a concise information. You can increase the more number of chunks here and then see the answer. But here, this is what we will build. It's very simple. The retrieval models plus generative models, they both combine in order to make the final retrieval augmented generation systems. So now what we will do, we'll get into the implementation of it. I hope you have already installed Postgres database. You have set up a database. You have installed pgvector as an extension. So because we'll be using pgvector as an extension to implement some of the processes of it, and then query the database and all those things. So let's go ahead by first of all setting up something. So I hope that you have already have the database set up, and I have a lot of tables. You might see not these lot of tables, because these lot of tables will be created in the next project. I'm going to use the same database which I'm going to use in the next project. Is I create a table. So first of all, I create and enable the extension of pgvector. You must have already installed this already. So if you run this command enter, it says pgvector already exists, skipping this, right? So it already creates the extension. So because you will be seeing where we'll be using it. So it enables this extension of pgvector. And then what we do, we want to ensure all our information embedding, because if the question comes in, the question will be converted into embedding, and that will be compared from every embeddings of the chunks. So that has to be stored somewhere, so that every time it comes and then we see it. So basically we create a table, document chunks, where the content, where we create ID, right? And then the another one is content. Content is about uh, uh, the chunk, and then embedding. And this is one of the data type of pgvector. That's what enables pgvector to be this much powerful and makes more efficient, because if you because a SQL does not accept vector as in data type. So you say vector for 1536 dimensionals. So 1536 dimensional vector. So we create another column embedding into this database, another feature into this database, which will have a data type of vector of 1536 dimensions. So I want you to see it, how does it really look like, and I'm going to document chunks. And because I've run it several times, so that's why it has added that database again and again. But over here, if you see, artificial intelligence is the simulation. This is one of the chunk, and this is the content of it, and the embedding is 1536. So if you do it manually, if you do it, it will, because if it is 1536, we need a specialized operations to do it efficiently, such as we need to make sure the indexing happens correctly, we need to ensure that similarity search and all those things. So pgvector eventually helps in doing your similarity search better, in doing your similarity search better, and other important things. So the same way, you have the another one is the embedding, and in this embedding, what you have is you have 1536 dimensional vector. Okay, perfect. So we'll come to that, how these embeddings are created using the code, but this is how it will look like, where you have the content and the embedding for the same. So now we can get to the code. So once you have created the table, that's enough. I hope that you already have. Now we need to set up some of the variables. We need to set up some of the connections, so that can be it can be written over here. What I'm going to do, I'm going to simply delete all the information from here, so that how can I delete? Let's delete everything. I'm going to delete from here. So what I'm going to do, I'm just going to create a different one, because let's say new, so that this is okay. So another one has been created, right? Discard all the changes, right? I'll just, because I don't have a pro, I'll go here. Now you can see that the database is complete empty. Now what we'll do, I will simply show you how you can fill this database and then follow this step to build this step-by-step procedure. So now let's get on the next one to start off with this. Now what we will do, we'll start working on the project. And over here, the first step is that we need to install necessary imports. We need to import all the libraries which is pretty needed for this project. And the first library which we're importing is nothing but OpenAI, which is a library which we'll be extensively using. I'll just do one more. Yeah. So OpenAI library, which will help us to generate embeddings and which will help us also in generating the response using generative models. Then we're going to import PyCog2, which eventually helps us for connecting and interacting with PostgreSQL database, because we just now has created a database, so that has to be connected with this particular system. So we are going to use it. And then we're going to use Streamlit because we'll be making a dashboard from it. And then we have something called register adapter, because there are several environment variables. Of course, we'll be not using it too much, so I just imported it. OS, which will eventually help us to load the environment variables, because there are some keys. Because see, I cannot show you my API keys. If I show you, then you'll be maybe you can misuse my API keys. I can't show you my database name. So to protect it, I've created .env variable where all my keys, important keys are, and then where I'm retrieving from there to here itself. That's it. So we need to load the environment variable from .env file. So that .env file is important from here. Now you can use os.getEnvs, because first of all, you need to configure your OpenAI API key. So you can find the OpenAI API key. Now, if you don't have a credits, we have announced a credit system till 31st, 27th, I think somewhere around that time. So you can use that. We are giving away $6,000 worth of credits to all the students who are interested into it. So you can go ahead, feel free to fill that form. You'll be getting it ASAP, any amount of credit for sure. Now, over here, you can get the API key and then you can paste it over here. Of course, I'm importing it from OpenAI.env variable, file, where the key is OpenAI API key, which is equals to the key over there. Now I'm using PsyCog2 to connect to my database. Now, you must have already getting all these details when you're setting up the database, which is your database in table plus. So which is your database, what is the username, what is your password, what is the host, what is the port which you're hosting. And then you have conn.cursor, which allows you, so this cursor, which will allow you to establish a connection to this PostgreSQL database, where these are the particular details to identify the database details. And then it will help you, this cursor will help you to execute any sort of instructions, because we need to run several SQL queries to embed or to retrieve and to make use of pgvector. Also there is pgvector Python library also, but for the ease we'll be using SQL pgvector extension itself into this. Now, as I said that I've already created from the PDF to a sample of chunks. There are 3 chunks only for a simplicity purposes. I've created over here. You can add more chunks. You can add a PDF, and then you can define a function that takes the PDF and converts that into several chunks, because that will be doing into the next project. And then we are using Streamlit to have this title of interactive Q&A system, this and blah, blah. Then what we are doing, the first step is document chunking. So we are going to each of the documents with the indexing. That's why we are using enumerate function. And then we are going to write every chunks from the doc which we retrieved. Now what we will do, we will generate and store the embeddings in the Postgres, of course with the user display, because we'll be showing you, because the main point was to make this particular Streamlit is to show you step-by-step procedure. So because we need to show you, that's why I'm going to create a list of embeddings also. Now what I'm going to do, I'm going to go through each doc into that particular documents list, because these documents list is a set of list of documents. So we're going to each document over there, and I'm going to use openai.embedding.create, and I'm going to use the text embedding ARA002 for the taking out the embeddings of my each text, and the input would be that particular document. And then what I'm going to do, I'm going to append, and then I'm going to retrieve that embedding from this response, and then I'm going to append the embedding into this embedding into this list. And then what I'm going to do, I'm going to also, because this is for showcasing purposes, and then what I'm going to do, because we need to store the embedding so that similarity search is easy, I'm going to use the cursor, which is my Postgres, which establishes my connection with PostgreSQL, and I'm going to execute one command. I'm going to say insert into document chunks new. What I have to insert? I have to insert first of all the content, which is my chunk, and then the embedding. Now, the values of that would be first the document, the chunk, that particular chunk, and the embedding of that particular chunk. So it will add, and then it will run the loop again, and then it will add my another chunk, and then so it will keep on adding, and eventually it will also showcase you on a Streamlit, and then it commits these embeddings to the database using con.commit. And now once we have the embeddings done, then what we do, we eventually go ahead and then get relevant chunks. So before that, we need to have the question so that we can retrieve the relevant chunks. So we get the question, and then how many chunks we need to retrieve is 3. For simplicity purpose, I've written 3. If you add more documents, then you will get a lot of stuff from there. Now it generates the embeddings for the questions. So the first step is question embedding response, where we are going to use the same embedding model in order to retrieve the response of the embedding of the question. Now what we do, we eventually take the embedding by the response of it by going into the data and then going into the 0th index and getting the embedding from the response, because there are multiple outputs into this, so you just need to get the response. And then what we do, we query, and that's where this is one of the helpfulness of pgvector, where embedding was your column of vector, and that's why you're able to insert your 1536 dimensional vector over here. Now there's another powerful feature where you can use the pgvector operator of this pgvector similarity operator, where you can use to get this top 3 similar scores based on your questions. So what we say, we need to select that content, select the content feature from this particular document chunk new database, and then we need to order by the embedding by taking the top similar chunks using this particular pgvector similarity feature. And we need to only limit it to some top 3, top 4, top 1, whatever. So this %s, which tells you need to get the embedding from the question embedding. And then because the question embedding is this particular embedding, so you need to get this, compare all the embedding with this question embedding, and then find the top relevant stuff. And this is the powerfulness. It will do it very quickly just by single operator using pgvectors operator. And then you can fetch the results, whatever the output which comes in. So you see a particular output over here will show you, you will get all the relevant chunks, and then it gives you the relevant chunks. And then if the question, so first of all, we also show you the embedding for the question, and then we get the relevant chunks. So we call this function, because this was a function of get relevant chunks. You give in the question, what was the question asked, and then say top relevant chunks which was retrieved based on the question was following 1, 2, 3, whatever. I mean all the relevant chunks. What we will do, we'll simply set the default to 1, because I just want to see 1, because there are only 3, so I'll just take 1, and it will show you the top, because this is showing is just for the learning purposes. And then once you have the relevant chunks, what is the next is using the generative model to generate an answer, right? That's pretty much it. So what you do, you use GPT 3.5 Turbo to get the relevant chunks, which is out here. So you first of all prepare the context, because you need to give all the relevant information to the generative model so it can use those relevant information to make an answer, right? So what it does, it takes the context, and the context is nothing but your relevant chunk. That's it. I mean, the relevant chunk which was retrieved over here, that's what you get. It's not an embedding, it's the concise text which was received after calling top n sort of thing, right? And then you write a prompt. Prompt is an essential part of generative model. Prompt is a way to communicate with your system. So just like you use GPT to write a beautiful prompts to get an answer, the same way. So you say using the following information, you have the context, answer the question, and you also give the question so that it has the context. So this question you have, and this is the context you have, so please answer it from there, and it will be efficiently able to answer. And then what you do, you use this prompt and then you create, and then you call openai.chat completion. We used embedding previously to create an embedding. Now we are using generative model of OpenAI to create a response by using the model 3.5 turbo. And then we are stating that this is the prompt. First of all, the role is system, that you are a helpful assistant. This can be majorly enhanced by your prompt engineering technique. And on the user side, we need to have the prompt over here, right? And then it eventually gives you an answer. That's pretty much it. There are several parameters of max tokens, temperature. There are a lot of stuff which comes across it. So please feel free to visit their particular, there are several documents around it, but it's very simple. The system, just to explain you what this parameter means, the messages parameter provides the input to the model in a chat-like format. So that model knows that it's like a chat-like format, so that it sees the conversation, structure of the conversation as a series of messages. Now, what is the system message into this case? The system message sets the tone for the behavior of an assistant, how you should act. It should act like a helpful assistant. Now, it will not get printed to the model, but yeah, it will show that system has to act like this. And the user message provides the actual question, which I said the prompt into this case, which includes the prompt as well as the context in order to get the answers from the model. Then that's pretty much it. The max tokens into this case controls the length of the model's response so that it does not really respond too much. And the temperature parameter represents the randomness of the model's response, so that the lower, so randomness, what does it mean? So let's say if the lower values like 0.1 represents, it has to be more focused and deterministic. It shouldn't be too much random. However, if you want to give more creative to the model to be more creative, you can increase this temperature so that it creates more creative answer by its own too, not just by relying on the context. And that's it. You close the connections, because if you open, just like I heard a very famous YouTuber saying, if you open a fridge, you have to close it also. So you close the connection, all these Postgres as well as con connections. And that's pretty much it. You simply go, and now there is one more thing. You have to first of all set up .env, and then you have to set up an virtual environment by using this venv. And then you can run this source Q&A, because my environment variable is this Q&A. So all my stuff is being saved over here. For your example, environment variable nothing but helps you to keep everything intact and all these projects into one single file, one single source. So now what we'll do, we'll run this Streamlit Q&A system. Let me save it. Document chunking started. And here we go. So if you, let's do a little bit of, here we go. If you see from the database, this has been the output of it. So whenever you create the relevant chunks, or all the chunks has been created into the embeddings, and then it comes over here, it finds out the context and compares. So you see that document chunks new has been created. I hope it makes sense. I hope it really makes sense. I have not deleted this document just for a sake. First of all, I think there is some issue because it has been created several. So however, that does not matter over here. I just needed to show you how the chunking process looks like and all. So this was a very basic system which helps you to create a Q&A system, and this is how it looks like. Now what we'll do, we'll go to something known as LexiChat, which is our next step, and we'll create a system where you can upload a PDF and then chat with it with the relevant context inside it. It will also show you where the document has been taken from. I hope it makes sense. I'll be signing off. I'll be coming into the next one for the LexiChat. We're going to start with LexiChat, and LexiChat is nothing but a platform where you can come, upload your documents, like any sort of documents, and then what will happen, you can come over here and have questions about it, ask questions about it.
And then it will also have the conversational context so that you can go more deeper into their questions, just like the chat GPT, but it will give you the only information which is available into these PDFs. You can have multiple documents over here, and then you can also add tags. And the good thing is that it will automatically assign those tags by using an AI, OpenAI API model to eventually assign those tags which has been created. So there's a lot of things which we need to work on this. The first step is into the code, if you see, we'll start with something which is setting up our databases, which is setting up our nothing but how and where, the way which we need to store our information, and then we might go ahead with other pages. So this is complete where I'm focusing too much on code instead of live coding, because I do not believe in the idea of live coding, because there might be a lot of things which might go missing into that, and that takes a hell lot of time for you guys also. For you to understand, you can just understand the code in just few time, and then we have an ability to take out the code from the GitHub and eventually go ahead with it. So that's the chat with the documents, where you upload the document and any number you have with your conversation. You also get references from where the answer has been created. And then you also have the tags, and there are multiple things which we have embedded into this project. I'm super excited to get it started with this. Let's get started ASAP while coding this project. So hey everyone, now we'll go ahead and talk about something known as setting up the database, because this is one of the most important part of our project, where we will this code will eventually set up the database scheme for us, and we'll be utilizing a library and object relational library sort of thing in Python, which will help us to interact with our database which we are going to set up. And then we probably going to use something known as pgvector, because as I told, pgvector gives us an ability to store the embeddings in the most efficient and most variable way, and then possibly use this for a semantic search and a lot of things which we eventually had already discussed. So we'll be using those two libraries in to set up some database. But before we go ahead with why do we really need to set up a database, I want you to take through this example. So I know you have already seen all these streamlets and stuff like that. So over here, when you actually upload the documents, it should be stored somewhere, right? It cannot be just uploaded and then went away for just one time. Even if I come back tomorrow and open the system, it should have this document. So this has to be stored somewhere when this gets uploaded. That's the first thing, right? Because if it does not, then if the questions are being asked from the document, it will be not able to retrieve the document because it has not been saved. So we need to save it somewhere. And then another one is something known as business, which is the tags. So we also need to assign the tags to this particular document so that it has an easy categorization and sort. So it would be pretty easy. So we need to store those tags also, the already existing tags which you have created, so that we can take these tags and compare with the documents which have been uploaded and assign those tags to those documents which relates the most. And that's why we need a database for the storing of the tags too, right? And of course, documents where we'll store the name of the documents, the tags related to it, and possibly the most importantly, embeddings of the chunks which is created from the documents. So that's why we really need a database, and that's what we need to create some sort of a PostgreSQL database, and we'll be using PostgreSQL. So the way we need to create is we can either come to the something known as table plus and create the table over here itself, or we use a SQL query to eventually create in that way. However, we'll be using the Python way to create such tables and all, to make sure that we are on to the project page itself. So now, the first step is, which we need to follow, is we need to initialize some sort of connection with the database over here, so that it is able to come over here, click on tables, create new tables create new databases based on your needs. So that's what the create new tables in that database is based on your requests. So we need to really connect the connection to the PostgreSQL database. And for that, we'll be using something known as PEWWES, PostgreSQL database class environment variable to eventually uh, connect with the database. And then we'll be, as I told, that we are going to create .env file where we'll be storing all our information. So it eventually gets get env as a from OS, and then we'll be getting the PostgreSQL database name, and then followed by the host, port, user, and password. So I hope you have already set up this and you already know this. You can simply go to the env file and then just change it out there. That's pretty much easy. So now that's one of this is pretty important for setting up your connection. Now, what it does, it centralizes the database configuration. So it makes it very easy for you to retrieve, to easily connect with the database, and acts like an interface instead of you coming over here and doing it. So it's complete does things over here. So now we'll be creating three models. So understand, we are going to create three models. We are not going to fill anything. It's just that we are creating a three database models, three tables inside there, and then we'll be defining relationships between them. Like documents and tables will have some sort of relationship because tags is being assigned to those documents. So we need to design the design in such a way that it has the relationship between them two. So what we will do, the first step is that we'll be creating the documents table where we'll be storing all our documents into the PostgreSQL database. So what it does, this eventually creates a table called documents. It will eventually create a table called documents into this database, which we have recently connected with. And then the and using the text field sort of which we have imported from PWEE, which you can of course I'm not going to go in too much of detail, but it stores the name of the document as a text. So that's what the text field means, and that's what because it will involve only text, right? That's why it is known, and it is the text int field. If it is an integer field, that sort of thing is still valid. So over here the documents will be text field, that's why it is adding as a text field, while the database name will be documents followed by the database which has to be connected with the following. So this table serves as the main entry point for storing metadata about each uploaded document. So what it does, if you come over here and see the documents, it will store the first I've uploaded is meeting with Imoha CEO. So that is the which I've uploaded. So it will store the name of the document. That's it. So that's what the document says, that it will store the name of the document. The content is not yet stored. Only the name of the document is being stored at right now. We'll talk about when the content will be stored just in a bit. Now another one which we have the tags. The tags table will be also text field because when texts are being accepted, and the database table would be tags followed by the database which we need to connect is following database. So where you will be storing all the tags. So if you come over here into the tags, sorry, I think I really don't have, yeah. If you go to tags and then you see I've created only one tag which is business. So over here it has that tag also. So now over here, if you see, this is the tags table which eventually this is the tag table which eventually represents or stores different type of tags or categories that can be assigned to the documents. Now we need to define the relationships because there are two relationships where tags are being assigned to the documents. So we need to represent a many-to-many relationship. So we need to make, so this eventually document tags, which is another database model, another table for us, which eventually represents a many-to-many relationship between documents and tags table. So what it does, the document ID is a foreign key linking to a document into the documents table. So it's more like that we use the foreign key field, which is another method from the PWE, where it eventually what it does, it says that it fetch all the tags for a document. And then it automatically, so we also selling cascade, which automatically deletes related tags when the document is deleted. So let's say if you delete that document and that tag is associated with the document, it gets also deleted. It does not remains already. So what it does, the foreign key field eventually establishes relationship in the documents. So documents is the following, this table, and then is the backref, which is another one of the parameters which allows for reverse lookup, which is fetching all the tags for a particular document, which we call this as a document tag. So if you come over here, this is the document tags. So if you see the fifth document, the fifth ID of the document is related to the ID of it is the first. So if you go over here is the first, right? So that's what it does, that it eventually creates a document tags which eventually fetches and then assigns the following. So if you see the document tags, this is being created. So I know it might be confusing if you're new to it. Is basically that we need to link the tags to the related documents. That's pretty much it. Now, if you go ahead, the tag ID, the document ID is a foreign key linking to a document into the documents table. Now that is the document ID, so that we get the document ID. Now the tag ID is a foreign key linking to a tag in the tags table. That's it. So foreign key, if you'd like to know more, please go ahead and learn more about foreign key field. But it's basically make sure that we create such table where tag and document ID will be intelligently referring to each other, right? So if you upload a document, it will search through the tags and then use the tag ID, and then because you'll be seeing that will be when we eventually talk about suggesting tags based on the documents, we give out two IDs. The ID is related. So we take the document ID and then we have those ID, and then we eventually make that up and then add that into a document tags. So that's one thing, which is the document tags model. Another one is another database model, which we call this as a document information chunks. So what it means, it represents the chunks of the documents and their embeddings. And that's what is very important. So if you come over here and then if you see, is the document ID, and then this is the chunk, and this is the embedding related towards it, which is, this is the vector, this is a text or string, and this is the document ID, which eventually, if you come over here, documents, that is the ID. So right, so document ID, and again there's a relationship between documents and documents new in information chunks. So I don't want to talk more in detail. Why do we reduce into chunks? We have already talked into detail. So basically a particular document is then classified into chunks. So we'll talk. So currently all of these are the empty, what can you call, empty sort of database, right? Empty database. You will not see this into your file unless you run something. So you have this, and then there are multiple chunks which has been created, and every chunk will have its own embedding, and that's what it says, that it uses again foreign key to establish a relationship, and then it also adds backref document information chunks, which what it does, it's the foreign key field is the document ID which we are coming up with. What it does, it links the chunk to its paired document. So if you see, this is the chunk of this particular document, this is the chunk of this particular document ID. That's what it does. And then another one is the chunks, which stores the actual text of the chunk into that database. And then we have the embedding, which is like a vector field which stores the 1536 dimensional vector representation of the chunk. And then you create a new database model known as document information chunks. Then that's pretty much it. So that's what we do. We vector field, which is provided by pgvector extension for Postgres. It enables efficient similarity searches. That's why you have seen in the last project also that we use something known as vectors to eventually create an embedding column. So something new is over here, that we are linking several databases to interact with each other. And then what you do, you're creating tables. So what it does, it connects to the database and it creates the necessary tables, which is documents tags, document tags, and document information tags. Sorry, chunks. So that's what it does. It creates the necessary, that is, which will be completely empty in starting. And then it creates the table by this. Now we have another interesting function known as setting up an open API key management. and that's another major stuff. So what it does, it configures the OpenAI API key directly into the PostgreSQL for usage in the queries. So when we talk about generation, generative models, you'll see that how we are using directly this from the directly PostgreSQL query using the help of PGAI to eventually go ahead and because we have already enabled the pgvector extension, it gives us an ability to directly query any sort of like if we want a response, we want to generate an answer from OpenAI, we don't need to write this extra code, we can just write a one-liner SQL query. That's why we'll set up here itself, and then I'm getting the OpenAI key from my environment. So what it does, it you can use for some database queries like generating embeddings. We'll talk about when we talk about generative and retrieval thing, we'll talk about how it is being handy. So it uses OpenAI directly, and then we'll be storing the API key, ensures that it has the proper integration. So how it comes all together? The documents table which you have created, the first one, what it does, it stores the metadata about uploaded documents, which means the ID and the name of the document. And then the tags table, which stores the available tags for categorizing of the documents. And then you have the document tags table, which links the documents to the tags, which is enabling flexible categorization. And then you have document information chunks table, which stores the document chunks and their embeddings for efficient retrieval. So what it does, it just stores the document chunks as well as their embeddings by creating a chunks ID and as well as the related ID. Right, and we need to, as we are establishing relationships, so it has to establish eventually a relationship with the parents document. Okay, perfect then. So this was it about the databases. So now you have eventually created the 4 to 5 databases right now. So if it is one, it is eventually 4 database, and then you connect and then create the tables. Now what we will do next is we will talk about how we eventually start to fill this database. And I hope that you already know how this actually works. So I don't want to get in more detail about it. But what we will do is we will go ahead and learn something about how to fill this, which is retrieval systems and then generative systems. These are one of the crucial parts of it. So we'll go ahead and then eventually design our manage documents first, and then we'll go to the chat with documents, and then we'll go to the manage tags, and then we are mostly be done. But the manage documents is one of the most important part of it, because here what you're doing, you're converting you're getting the embedding, you're actually filling up the database when somebody uploads the documents, how the documents goes to a phase of chunking, and then how that goes to embedding phase, and basically we'll be filling up the database. Currently our tables are empty, so we need to fill that up with the relevant information. So whenever somebody comes over here, how exactly happens over here, so we'll talk about that in the next one. Go ahead and talk about the another major processes, which is how we are handling the managed documents, and it will be very similar to you that how you'll understand this. First of all, I want you to ignore all the imports. It might be very lengthy to understand it right now. So once you go more again and again, you'll automatically start to understand all these what are these imports and all. I don't need to go into the details right now, but just to give you one small detail, we are going to use Streamlit. So we're going to say set page config. The page title would be the managed documents. As you guys, you can see the managed documents, and managed documents the page title, and then the title of it would be the managed documents, right? And then we'll come back to delete document in a bit. So we are defining a function where it deletes the documents. So what it eventually does, it will we have this function eventually deletes a document. So basically you just give the document ID which needs to be deleted, and then we have imported our database of documents from this database file. So what it does, it goes to these to this documents.delete, where the documents.id of the document is the ID which has been passed, and then eventually execute this particular statement. That's what it does. It is not currently being used. This is a function which I'll come back to later. So now what we're going to do, we are going to talk about how eventually we want to go ahead, right? So the first step is what we will do will because the document can be multiple pager, and as I say, for the first step, because we were talking, the first step is converting a PDF into chunks so that computers can understand or generate meaningful meanings or facts from it. So the first step is we'll be doing document chunking. That's the first step, and second was be the extraction from the large document. So basically, if you convert the large documents as a split into smaller chunks, what it does, it converts that bigger one to smaller chunks, and then you still have the smaller ones. Now you use an AI or use AI models like GPT-4 or Mini or something like that to convert those smaller chunks into meaningful or smaller text statement to extract facts or key pieces of information and removing irrelevant information from it. So what you're doing two layer of thing. The first layer is converting bigger into smaller chunks, and then you're using an AI to say stating that, hey, this is my chunk. Can you just take out only facts or key pieces of information from it? And that's the prompt which you give to an AI by giving this chunk, and then eventually it does it. So if you see over here, if you see over here, this is the chunk. This is there must be bigger chunk, right? This has been converted into only the relevant thing, only the relevant fact or the important piece of information. That's correct, right? Now, what we will do, the key parts of the project, key parts of the code I'll go through. I'll not go through each and every integrity of the code because I hope that you already know. If you don't, please use GPT to understand any line of the code. Now, we have something known as ideal chunk length, which is the ideal chunk length, which means what should be the ideal chunk length of this. The facts which will be generated, what should be. After you convert that into this bigger one to smaller chunks. Now, smaller chunks to more factually correct and as well as key piece of information, what should be? It should be around 4,000 characters. You can play around it, but it ensures compatibility onto it because smaller chunks are easier for the AI to analyze and return meaningful insights out of it. So I want to give you an example. So let's say there's a 12,000 character document. So it will be splitted into three chunks. Characters 0 to 3099, characters 4000 to 799, characters 8000 to 11099. So the three chunks will be created out of 12,000 character document. So now we are coming to the next step is we are going to create a table sort of class or sort of model for generated document information so that this list, whatever the facts which are being generated can be taken into the facts and which can be later inserted into the database, because that's what we ultimately want to do. So let's go to the generate chunks because that's another logic which we want to talk about. So what it does, this function generates a facts from the chunk of text by sending it to the OpenAI APIs, basically GPT model, by giving them smaller chunks to come to more key pieces of information or facts. So we are going to use async which is asynchronous function over here into the function. Now what it does, it allows the systems to perform other tasks like processing other chunks while waiting for the API to respond. It's in some time API may have a high usage and it might be that it is not allowing other chunks to be created. So what it does, it performs other set of tasks in the meanwhile while waiting for the API to be responding. So what it does, it eventually improves the efficiency and responsiveness when processing multiple chunks. Like if you upload 10 documents, it will be, if the first is not happening, it will go to the second one. If it will second, so it will keep on performing other tasks instead of just staying at the first and waiting for it to complete. So what it does, while true, it says that keep on trying, which means the total retries keep on trying, because sometimes what happens that what eventually it ends up happening, that network requests can fail several reasons. It might be rate limits, it might be timeouts, it can be their own server issues, it can be a lot of it. So we are adding a retry mechanism so that it ensures that temporary failures do not stop the entire process. So we just want to make sure that it does not stop the entire process. So what it does, the loop retries at least 5 times with 1 second of delay into it. So that eventually goes ahead, but this is so if you see over here, the total retries goes to
the 5 times, because that's what the try and we try and accept. It goes through it goes through till 5 and eventually waits at least for 1 second. And if it still does not happen, then it says fail to generate the facts for the PDF chunk with this error. That's it. So it will yield an error. But what if it does not yield an error, and then you what you do? You send a request to an OpenAI. To this sends the chunk of text, which you have the chunk of text which you eventually took from the PDF, and it will be on a loop. Okay, it will be on a loop. So you need to send them the PDF chunk, and then it will be the chunk of the PDF. It's not the whole PDF, the chunk of the smaller, the bigger PDF converted into several chunks. The first chunk will be sent to it, and then you'll be calling using an OpenAI request to the OpenAI, where we'll be using our model, which we for the processing, and then we're going to give the messages. It will be having two instructions. First is the role of the system and the role of the user. So first of all, you give the system the role, right? You give the system the role, which will be the system. Now into this, you eventually pass the what can you say? You set up an AI with a task specific prompt. So if you see over here that I've imported something that's from constant imports create fact chunks. So you need to tell the model what he needs to do. So if you come to the constants.py, you have something that's create fact contents, which says you're an expert text analyzer who can take any test, analyze it, and create multiple facts from it. Output should be strictly in the JSON format. That's what it does. So sorry. So that's what it does. Now let's go to, yeah. So what it does, the role of the system is to do that, is to create such facts. So that's what it is, importing the prompt for there. You don't need to come over here every single time. You can just go into the document and change the prompt, and prompt changing is really a magic in drastically improving the performance. Now the next one is the role user, where you're providing the context, where you're providing the actual task to do, which means you have to do this by you, and what the user would be that will give you the PDF text. So basically, it passes a chunk of the text as an input from the user side, and the task would be to create the fact system prompt. You have temperature, which says that it controls the randomness, which means lower values make the outer more deterministic. You actually prevent the ways of being more creative, and it should be in the JSON format, JSON object. And what we are truly doing over here, if there's no facts generated, we are validating the response. To make sure that the API returns the valid data, we need to do this particular checking. So if it does not, then it raises an error of no facts generated. Then what we do, we eventually takes up our we eventually validate our response. We validates the JSON response using the generated document information chunks model, which we have eventually created over here. It eventually validates the model, validate JSON, the content out of it, and the facts out of it. That's it. And then it says generated the length of the information documents from it. It will be eventually converted into a list, but it also validates. It says the length of the list would be this much facts for the PDF chunk. So if you see over here, so whenever you upload a document, it says generated 3 facts for the PDF text chunk 8, text chunk 9, generated 3 facts. So it will keep on generating those facts for each of the chunks. That's one. And as I said, it keeps on retrying. So this is about generating chunk, where it eventually converts the bigger one into the more concise factual information, key pieces of information. Now, once you have this, we need to assign the tags associated to these kind of chunks, to these kind of documents, right? And that's another thing which we have to do. And then what we will do, we'll talk about how we can combine both tags as well as this particular generate chunks, and we also have to convert those chunks into the embedding, because that's what the retrieval, we have to convert all the documents into the embedding, so that whenever the question asks, the embedding of the question and then this document's embedding will be you using the similarity search, you eventually match it. So let's go to the next one as soon as possible. Now we have, once we have completed this particular, where it takes the PDF and converts those into chunks, we also have one feature where the particular document has to be attached
with the tags. So for example, if you come over here, I have created a tag of business, or I can create tags, let's say different tags over here. So whenever you upload a document, I upload a document with Moha, eventually has the tags of business. Now, if I upload something else and I add the tag of food and then I upload that, then the food tag will be automatically associated with it. And that's why we need to generate the sort of tags out here. So first, which we did eventually was to convert the simple PDF into chunks, and then we actually want to assign the tags to its respective document. That should be correct, right? So that's what we are trying to do right now, is this function which we have right now. Yeah, this function which we have right now over here, which is get matching tags, and again we are going to use asynchronous function, because the reason why I say this, because it creates several tasks, and it even if the API does not respond at the time, it continue executing further tasks. So to talk about this, what does this function does? In a nutshell, what it does, it extracts the semantic tags for a document based on its content. So if you upload a document, it will take out some semantic tags out of it, and then it takes those tags and matches with the existing tags which you have added into the database, into the add tag sort of setting. And then it returns a list of IDs from generated. So what it will do, let's say that you have a document like this, sorry, B C sort of document. So what it does, this function will eventually take out, okay, this is ML, the tags are ML, business, AI, right? But only business is available, so it will return that, okay, business is available in existing tags, it will return the business. So it will search in the database what tags are available, and it will eventually return something known as business. The reason why, because that's the tag which should be assigned, which we have created over here. Otherwise, it will keep on creating new set of tags, which can be very lengthy too for you also. So this is one thing. That's what the get matching tags does. So how it works? So just to give you a little bit of understanding, what it does, the tags is our if you see over here, tags is we are importing from our database the table. So what it does, it eventually fetches all the available tags from the database. That's the first step. And then what it does, it eventually goes ahead and converts the tag's name to the lowercase for case insensitive matching. So it converts all the tags to the lowercase so that we don't miss out on the common words. I hope you already know what is case insensitive mismatching. And the OpenAI model, what it will do, it will suggest those tag names which needs to be compared with the existing tags, which is which is available in the database, and then matching it, and then eventually giving the tags to a particular document after having match. So I hope that's correct. Now, if there are no tags, then it will return if there are no tags into over here, then it will not do anything. So it will return an empty list immediately. So if your database has no tags, then there's no point of creation of any tag. So we eventually say that it returns an empty list. So without this, as I say, there's no point to match the document content. Then we start our asynchronous OpenAI API call. So the total retries, and then we're going to retry for at least 5 times to generate the matching tags for the PDF. Okay, this is not for chunk, for the PDF over here, and then we'll keep on doing it with a 1 second delay. That's what the try and accept error is saying, and then we'll keep on doing it. That's why while loop is here. Try, and then what it does, is it sends a request to the OpenAI client, so which you can see that we have imported from OpenAI client, and I didn't went through this particular OpenAI client. So OpenAI client, where I have already set up the OpenAI, which you can call this particular client to for any point, for generating answers, for doing literally anything. So it's like OpenAI, async OpenAI, where you get an API key, max retries and all. So you're basically using an OpenAI client sort of thing to call this API, right? So that's why you import from OpenAI to import OpenAI client. And then you call this OpenAI client to OpenAI API request
to suggest relevant documents based on the document content. So what do? You use GPT-4 or mini model, and then the system would be get matching tags system, and then dot replace tags to match with, and then str tags. So over here, what you do, what you do, it gives the model the task, it gives the model context for a task. So if you go and see the constants, so constant are you're an expert, so this is the prompt which we have to give to the system so that it knows what needs to be done. So it says you're an expert text analyzer that can take any text, analyze it, and return matching text from this list, which means from this database list. And then that's the tags to match with. That and tags to match with is already which we have, from which we have converted into lowercase. And that's why we have this placeholder variable which has been converted into strings, all those tags. So it says from this list only return those tags which make sense according to the text. Other output should be strictly in the JSON format. And tags 1, tags 2, tags 3, up to tags 3. So this is the prompt where we are saying get matching tags system, where we are taking the prompt and then we are replacing the tags to match with placeholder with the tags which is already there, which is the lowercase, so that it only returns the matching text. This is the task. Now the role of the user that's the role of the user is provides the actual content document text for the analysis. Right, and as I said, all these remains variable the same. So what it will do, it will take it will know the task, it will know the PDF text. Now PDF text has to be inputted into this function, and PDF text wouldn't be the most famous what can you say, I mean chunks. I'll talk about, because PDF might be 1 lakh character, 1 lakh word sort of big word. So, but you can get understanding of what this document is in just few sentences or few words or probably few paragraphs from the PDF itself. So we don't really need those and then utilize our resources for the same. But continuing our conversation, what it does, if it validates the response, which means it ensures that API returned a validating response. So if the response is empty, if the response is empty, then it's an empty response for generating matching tags. And then what this generated matching tags, which we have created a class over here because we need to put our classes over here, tags into this particular list which can be committed into the database. So it says we need to validate so what we are technically doing, we are using the generated matching class. We are using the generated matching class to parse the JSON response. So that because it yields us the JSON response, right? So to parse this JSON response and then extract the suggested tags out of it. That's what this matching tag names are saying. Now we need to get the matching tags IDs. The reason why I say this, because if you come over here and see the document tags, you need to matching tag ID. So this document has the matching tag, that is 1, and document 5 is related to 1. So that's what we need to do. So for each suggested tag, so we taken out the suggested tag from the OpenAI response. So it goes through each suggested tag into it, and then it finds its corresponding ID. Now, if a tag is not available, exists in the database, which means it has not taken from the list, then it throws an error. Right? I hope it makes sense. So it eventually finds the corresponding ID into the database. So if that is available, if matching tag is there, then it appends the ID of that matching tag into the matching tag IDs, the list which you have created, which of the type of an integer. Otherwise, it reaches in match not found in the database, right? And then it returns the matching tag IDs that has to be returned. So currently it is just for, so you might be understanding how it will work and all. So we will see when we code it out into the pipeline, so that whenever a document uploads, you will see how the process looks like. So now the tag system is done. I hope it makes sense to you. Now what we will do, we'll take all these two functions which we created,
and put it into something which is known as upload document. And that's another major function which I want to talk about, that what this upload document does, and then how we can eventually make it used to make it end to end, where it converts the PDF into chunks into embeddings, and then creates the tags and then attaches the tags to the document. That's what the aim of the upload document, and that's what we will end up to. Now we will go ahead and combine those two functions. We'll go ahead and combine those get matching tags and get chunks asynchronous function to go ahead and uh, uh, take if an document is uploaded, then you will see how the step-by-step process happens, and what in every document the step-by-step process happens. So the first step is that what we will do, I'll try to, whenever the PDF file is there, then the PDF, we use something known as PDF to text libraries. That's what we have imported. So we use PDF to text library to convert the PDF into the text. To convert the PDF into the text, which means it converts the PDF pages into a list of text strings where each string represent a page, whatever the page is. And then Bytes IO, what it does, it wraps the uploaded PDF file into the byte system to pass it to the PDF to text library. And then what we say, we want to, after every page, we want to join with this \n, which combines all the pages into a single string, separating them with this. So all the pages, with there are multiple strings, so it combines all of them. We're separating with this the /n. So here how it works, you have this parsed PDF, you have this parsed PDF which eventually we get, and then this is the text which comes to us. So you have a paragraph, and then the first step happens in converting this into the several strings, and then you combine all the strings into a single string by adding this separator, right? And then what you do, because you still have to convert it into the chunks, so you create a PDF chunks with a list, and it should be a type of str, and it's an empty list. So you go for I in range. So what you for what you say, that I want to go through all this length of the PDF text, and I want to split the text into the chunks. So basically that's what we are trying to do over here. Is it calculates length of the PDF, calculates the total length of the combined text, and the loop splits the text into smaller chunks of ideal chunk length, which is 100 characters or maybe 400 characters, whatever the ideal chunk length which I have defined. I think it's 400 characters, 4000 characters, sorry. So it goes through it calculates the total length of the combined text, and then it splits the text into the smaller chunks, right? Smaller chunks. And then what it does, it appends into this particular list by slicing the text from the current index to I plus 100 index. So I plus 400 index. So basically it just takes out, so if you have the 12,000, then it takes from 1 to 4,000, then 4 to the next 4,000, 8,000. That's how it is working right now. I hope it makes sense now. Perfect then. So you can do the dry run if you want, but that's what converts this into this particular chunks by converting them into several 4,000 characters each chunk. Now we need to prepare those chunks for the processing. Which means now you have converted the big PDF to smaller chunks, but now that smaller chunks has to be converted into more understandable with key pieces of information. And that's what we were doing in the generate chunks, where we are calling the OpenAI API and stating that, hey, you're an expert, and then please give me only relevant information. Right? So that's what we are doing over here now, is we are going ahead, and then we are asking for generate chunks for each chunk out there, and this is an asynchronous function. That's what we are creating a list of generate chunks coroutines, and what it does, it simply stays, it's a naming convention, to be honest, to name it that we are calling an asynchronous function. So asynchronous function will get the index of the we will give the index to it, as well as so index which we will get from the enumerate thing, and enumerate because it enumerate provides and of the PDF text chunks will provide the index as well as the chunk. So because we have all these, it will look like this, something like this PDF text chunk. So it will also have an 0th index, first index, second index. So it will give you the
index also. It will give you the simple index also, as well as the chunk related to it. And then it generates the chunks by giving the index of this and then the PDF text. So it does not generate right now, it creates the tasks because it's an asynchronous function. So what it does, it creates the task, and then task has been created for it to process them asynchronously. So that's what it does. It creates those tasks for it over. It's a complete production level thing. So you can see it is not doing it right now. It is creating the task by calling this for each chunk by taking the index in the PDF text chunk, and then eventually converts that chunk into the simple or key pieces of information only for that particular chunk. I'm talking about just one single document at this particular point of time. So you will end up having the generate chunks coroutines will have this following. The list will call generate chunks for all the chunks which has been created. So this is just a dry run for you to understand it. Right. So now we'll go ahead, and then we have something known as, and just to tell you why there's a coroutine name, because it represents what the variable stores, right? And that's why which is used as a what can you say? It indicates the elements in the list are asynchronous tasks, not function calls. So if this looks like a function calls, but these are not. These are asynchronous, right? Perfect then. Now we will go ahead to the next one, which is once we have this tasks which is created for the PDF converting the chunk into these key pieces of information, we go ahead and set up something known as when we run those chunks, when we run eventually those chunks. So the first one is this event loop. So what does it do? So asynchronous, if you see, we have imported async library out here, and then we are creating a new event loop because that has to be run on loop, right? That has to be run on loop. So what it does, a new event loop is created, and then this loop is responsible for executing asynchronous tasks. So it's like in control room where all your tasks are going to be managed. But you need to assign someone. You need to assign someone to give a permission. It's like a telling you need to assign someone to use this control room to execute tasks. There can be multiple control room, but you want to tell Python that you need to use. So you say async.set event loop of this particular event. So you have to use this particular control room to execute all the tasks. And then this, what you do, you use gather to eventually get all the asynchronous tasks which we need to run. And it will get you all the coroutines or the asynchronous task from this particular async, because this yields this. So it will all yield all these asynchronous tasks to be executed. And then what it ends up do, that it waits until all of the tasks are completed. Into this case, it wait until all these three asynchronous task has been completed, and you have all the generated chunks contains over here, right? And then you do the same with get matching tags routine. So what it does, you call the get matching tags, and you only pass the first 5,000 characters, because you don't need to pass the whole thing. You just need to pass the first 5,000 characters of the PDF, and then you'll be getting the tags associated with it. So a coroutine is created to process the first 5,000 tag characters of the document for the matching tags, and this is a separate task from the chunk generation. So now what it does is the event loop which we are creating is to run until completed. As I said, the first it will run this, and then it will run the next because there is only one async task, but there is multiple asynchronous tasks into this. So we are using the control room to run until complete, to execute tasks and wait until all tasks are completed. So here only two tasks are there, which is generate chunks, gather, and get matching tags. So that's this one and this one, and they will have their own list which has this has three tasks into this, and just it has one task. which has to be completed. So all of them starts in a parallel. So it's all already done for you. So all parallel execution will start, which is generate chunks for the first, generate chunks, all these three, and then and then the matching tags. So all will do it parallelly to make it faster, efficient, and everything. And then you eventually get this particular, if you run this particular, if this event loop is run for that, you will get something which is the fact chunks 1, fact chunks 2, fact chunks 3. So basically it precises the key pieces of information and gets you 3 again with the more precise information. The output basically output of this asynchronous function. And then you have the matching tag IDs, because that's what it returns, the matching tag IDs, which what it does, it eventually finds out those tags which are available in the database. Also it analyzes from document, eventually returns those IDs which can be associated, which will be associated with the document itself. So that's what it returns, and that's why we unpack both of this when we run this. So this will return you the chunks which are more concise and the matching tags IDs over here. I hope it makes sense. Now, the reason why we do this is you'll automatically understand. So this will yield you the nested list. So it will yield you this, the document information chunks will be something like this. Something like this. And your facts will be inside it. So we need to convert that into something like this. Right? Currently it's this. So that's why what we do, we create a single list containing all the facts generated from the documents. This is the line what it does. It converts the nested to the single one. I think that should work. So what we'll do, we'll create a single list containing, and that's what we do. And then you're having your facts generated from the each document chunk, and then you're having tag IDs that match the document content. And the whole point for running this asynchronous thing is to do the parallel execution and make sure that we save time, and making sure the generating and matching tasks are independent tasks. I hope it makes sense. So now what we'll do, we'll talk about the next stuff, which is inserting, which is saving all the generated data from it. That's the another one, because once you upload the document, then everything happens. You generate the chunks, you generate the matching IDs, but that has to be also saved, right? So we with db.automatic, atomic as a transaction. So what it does, it creates a database transaction context, and all the database operation inside this block is treated as one atomic operation. It as one atomic operation, which means it will be just for one row. You can understand in that way. Perfect. Right. So it first of all sets the OpenAI API key. That's what it does. It sets the OpenAI API key that you can see over here. That so that SQL knows that I can use this, because we need to now generate the embeddings also for the chunks, right? Right. So, and if any operation fails, the entire transaction is rolled back, because not a row is inserted, right? So we don't want empty rows. So if the operation fails, if this operation fails, then entire is abandoned. So this, what it does, this document ID, what we are doing, we are inserting a new row into the document table. We are inserting the new row into the document table, and then it stores the name of that uploaded document, and the name of that uploaded document, which has to be given from here, right? And then it executes it. And then we get an document ID, so that we can use that ID for several other purposes. So if you come over here, you can see it has been inserted, and the ID which we will yield from it, so that we can anywhere take it up. So for chunk in the document information chunk, so we'll go through all the chunks into the document information chunks, and the document information chunks are nothing but the lists of more concised information. So it goes through every, and then what it does, it inserts those documents. So document ID
as well as the chunk, and then the embedding of it. And that's where we are using something which is another powerful feature of PGAI, timescale PGAI, where we are using and directly calling an OpenAI inside the SQL and saying that and stating that uh, to generate me then embedding. To generate me an embedding by using this particular model, and then you should generate for this particular chunk. So it does for every chunk. So that's why it is in a loop, and then it executes it. And then that's the document information chunks. And if that's why you go to document information chunks, you have this document ID chunk, because there are multiple chunks for the same ID. So you have multiple IDs for the same chunk for these different chunks, and then the embedding associated with it. And then you have and then you need to insert your tags also. So what do? You eventually go ahead in the document tags table, insert many, because there are multiple things to insert, because there might be multiple IDs. So you say for tag ID in the matching tags ID, you have the particular document ID, because document ID, the tags ID is of that particular document ID, and as well as the tag ID. And then you commit those transactions, which means you push those transactions, just like you commit git. And it says inserted this much chunks for the PDF name with the document ID and the length of matching tags. So this is what you do, and then you eventually close this event loop. So that's what it does. I hope it makes sense. I hope the document uploads. So this is for a single document. So whenever the document comes, it converts the text into more chunks, then chunks, more precise information, generates tags for that particular chunk, inserts it by calling an embedding. So if you've seen that, we have also created an embedding also. So embedding column has been created without writing another separate code for it. That's why I say always these vector scales and time scale PGAI, pgvectors are super powerful. Okay, perfect then. So what we will do, we have a final part where we will convert this into an UI so that anyone can come and then they can upload and run all these functions. Now we are going to the last part, which is development of our managed documents dashboard, or development of the managed documents Streamlit UI. So let's go step by step. I think that you must be knowing most of it. It's just that I'll make it very quick. So we are going to create an interactive Streamlit interface for managing uploaded documents, which will include the functionality for uploading PDFs, processing them, and displaying the stored documents from the database and the associated tags, allowing the user to delete the documents too. For example, the thing which was uploaded, the tags associated with it, the uploading feature, as well as the delete feature. So over here, if you come, then you simply have this st.dialog, which we set a dialog option, which says define some modal dialog to what to write. That's what it does. And over here, it's like upload document, and st.dialog is a decorator to handle dialog interactions, because we have to literally upload something. So what this upload document dialog open does, so what it does, it implements the functionality for this particular document upload. So what it does, use st.fileuploader, where you upload the file and the type should be the PDF. If the file type is none, then what you do, you simply is not none, sorry, then you simply go ahead and then they click on an upload button, and then they eventually upload it, and then it will be simply uploading the PDF document. So it says that the reason why we say is not none, because we need to ensure it has been proceeded correctly, as well as we need to display those functions with the uploaded files names and the content. And then this rerun, sd.rerun, what it does, so whenever you upload a document, it just refreshes this page so that you see the relevant results out of it. So I hope it makes sense. And then you have st.button upload document, and then the key should be upload document button, and the function which should be is this particular upload document dialog open, which will be having the functionality when somebody clicks on this document. Now we fetch the documents from the database, I don't want to go into much of detail of what exactly we do over here, but in a nutshell, this particular document, what it does, it takes in the ID and the name of the document, and then gives out the document tags, as well as the names and the names of the documents and all. So it retrieves the stored documents and their associated tags from the database, and it uses a query to join with joins to connect the documents, document tags, and tags table to eventually get those answers.
So how it works is document.id gives you the unique ID of each document, and document.name gives you the unique name for, sorry, not unique, the name of the document, and a list of associated tax name. That's another one. Now what we do, this array.remove, what it does, this joins which we are having. So if you see that we have something known as array aggregator. So eventually what it does, it aggregates tags for each document into an array, removing any null value. So basically you can see that we are removing any null values out of it. And then you have joins. What it does, it ensures all documents are included even if they don't have a tax. So basically this ensures all documents are there even if they don't have the tax. And then it retrieves the tax name, which is over here, left outer join with tax. It retrieves the tax names links to the each document. I don't want to go in super detail about SQL. You just need to understand it's more sort of, it helps you store and retrieves to show the information over here. Okay, perfect. So if there are no documents, what it does, if there are no documents in the database, it displays an information message prompting the user to upload documents. So if you delete the document from here, you will see that particularly it will ask you to do it. So no documents created, please create one. But if there's the length of the documents, then what we do, we display it. So we go to document into the documents, we create a container sort of setting. So if you see the container sort of setting, where we are border is equals to true, and then we write the name, and then we attach the tags towards it, and then we also give an ability for someone to delete it. Now we have this option of a delete document. So if you come over here, it says you just need to provide the document ID, and what it does, it documents.delete, where the document ID was the ID of which was retrieved, and then you simply execute the command. That's why we written the delete document function in the verb. So I hope it makes sense. It was pretty simple to understand. So now what we will do, we'll simply go ahead with a chat with documents, because till now what we have done is we have created a system. When somebody uploads a document, the retrieval part is done, which means that it eventually converts that to an embedding, chunks and embedding. Now we need to create the generative part of it. So whenever someone asks a question, the question has to be converted into an embedding, and then it has to be compared or semantic search based on the embedding, and then eventually it should give an answer. So that's another part which is very easy, to be honest. So let's go to the chat with documents ASAP. So now we'll talk about our generative part, which is the chat with documents. So this is our generative part where we are going to literally interact with the documents which we have uploaded over here. So what we will do, we'll eventually go ahead and go step by step throughout the code. So completely ignore the imports right now, and you might not understand a little bit the essence of it. All is just for making it a Streamlit purpose and easy to understand. That's why. So it's okay if you're not able to understand too much about it. Just that I have used a little bit of Streamlit advanced stuff, which I would like you to learn a little bit about Streamlit and how we exactly create front end and all. It would be very easy for you then to understand. So we set the page configurations to chat with documents, and the title should be the chat with documents. That's what it is over here. And then when we possibly go ahead, is the message class definition. So for a structure of how the message object should be. So in a message, you have something known as the role, which is it a user or is it assistant, and content, which is what content it comes to, the actual text of the text, and the references, which says which chunks were used to create such answer, right? So this is the references. So we create a message. So any message will have these three components inside it. This is the structure should be. The reason why we do it, because we need to ensure that all messages in the chat flow follow a consistent format. It's like defining a template for storing your conversation data. Of course, we are not creating a database for storing our conversation data. It's just that we'll be maybe we want to, for at the moment, by the time I keep on opening this, I have this page open, it should at least have my all the conversation history, so that we can take in that account also to give an answer. So now we have something known as if messages not in session state, it should be, we create a new one. So what it does, it initializes the session state for storing messages. So by the time I'm opening this, I'm having the conversation, it should have it should have that all those messages already there.
So if it is not already defined, it creates an empty list every time we open this. So this session state ensures that for this session, the chats will be available. In GPT, it's different. It will be always available. Your history will be always available. But at some time, only one session. You have only one session where all the things will happen, and then once you go away, then nothing will happen. I mean, everything will be back to the normal, back to the it will not have any history. So that's what it does. It initializes the session state for storing messages where all the history of the chat remains there. And without this, what will happen, every message would reset every time. Like you send one message and then it will get a response and then it will rerun, which we don't require. We need a chat history also, right? So this push message, what does this do? What does this do? It is a helper function which we have created to append a new message to the chat history. So which we have created over here. So it should append a new message to this chat history. So let's say I have this one conversation, it gives a response. I have another conversation, so it should already also append that thing. So you will see how we'll use this push message in a bit. But now the major part, these are all for helper functions, just streamlit thing, just for showcase purposes. But the major part is this. So in generative models, what we have learned, first of all, we eventually take the question, we convert that to an embedding, and then we use a similarity search, any similarity search using pgvector to compare the similarity, and gets you the top 5 relevant chunks out of the already available chunks for that particular question, right? So what I'll end up do what I'll be doing over here is I'll define an asynchronous function, because again it is an asynchronous function because it runs things parallelly, and then we'll be creating an event loop to make it faster, and also that's what we will end up doing. So the user's input message is analyzed to find the most relevant document chunks stored into the database, and then we'll be using pgvector similarity search embedding to retrieve the top 5 matches based on the question asked. So let's go step by step over here. The first is that add pushing the message, which is, of course, you need to related document information chunks in the is the nothing but your retrieved chunks after the embedding search. And then you create one transaction, which is one SQL query. So you set an open API key so that SQL knows the credentials to interact with the OpenAI key, and then you get the result. So you from the table of document information chunks, which has all the document information chunks, what it does, it actually calls a SQL, and then it takes the embedding row, column, and then it calls an AI.OpenAI embedding, use PGAI, which you call this as a PGAI from timescale itself, and then you give the input message, because we need an embedding for the question which was asked, limit 5, and then we execute it. So in just single line, what you're able to do, you're able to do the similarity search as well as do the embedding for the question which was asked, and that is the power. And then what you do, you go through every chunks of it, and then you relatively append the chunk over here, and then you commit the transaction. I hope it makes sense. Now what we do because we need to push the message. So what we do, we have the role, the content is the input message, that is the question, because we literally have to push the keep on adding our conversation history and the references. So references in this case, I'll show you, it is nothing but your most favorite. So what I'll do, I'll simply upload a document, manage documents, upload document. Let's see if I have any good documents. Come here. Let's see if I have any other one. Yeah, I think I can have something. So let's do one thing. Possibly what we can do is we can come over here, and then let's say let's take some PDFs.
Okay. Upload a document. Of course, before that, we need to do few set of things. What I'll do, I'll delete this first of all, and I'll add a tag. And the tag which I'll add is nothing but water cycle. And then go to manage documents. I'll go over here and then I will upload my most favorite water cycle document. Click on upload. So I'll show you what it does. We'll have one conversation. Yeah. So if I could show you what's happening in the backend, it is generating matching tags. So it eventually generates the tags and then it generates it compares this and then generates the matching tags, which is the water cycle, which is correct in this case. And it is generating the chunks, which is generated 6 facts for the PDF for the chunk 1. And then it eventually adds that into the document information chunks out there. So it says inserted all these. Now we can come over here and then say, what is water cycle? Let's be very lame, okay? uh, what is the summary? So if you come over here, you will see that you are having something running up. But of course, so the lesson involves student observing evaporation condensation. So now when this happened, what it does, when the question was sent, which was converted, which eventually converted into embedding, and embedding which was used to retrieve the relevant documents and then the references. So in the message object, what is being stored is your question, input message, your simple content, as well as the role, as well as the references. And these were the retrieved top 5 matching chunks, which was taken from the pgvector, which was this statement which eventually got us right. So now over here, this is the first thing that's the first thing happens. But how do we really generate this response? Now we have generated the relevant chunks, but how do we generate it? We again do the same thing. We keep on trying because API might fail some time in between, but we need it to be running. While true, it's in for 5 times at least with 1 second delay. It says that we will call an OpenAI client for GPT-4o model, the system, and the instruction which is given to the system is respond to the. So if you go to the constants, what it says that you're a chatbot who has some specific set of knowledge and you'll be asked questions on that given the knowledge. Don't make up the information and don't answer until unless you have the knowledge about it. Knowledge you have is following. So we give them the context, which is the relevant chunks only, right? So if you come over here, so if you see that we go through the chunk, then we only give the related document information chunks. That's it. That's why we say just take the knowledge from here only. And that's why it is so powerful that it gives you an updated response only. Right. So it handles such things, and then the system message which defines the bot role, and the user assistant message which eventually defines the content, which eventually defines the things, the instructions to be given with all these parameters, right? And then whatever the response is, the message content is taken up, and then if there's no response, we don't do it. But if there's a response, we push the message. The role is the right now assistant, because the user was pushed over here because the input message in the chunks. But now what is pushed is your assistant as well as the response. And the references is none into this case as of now, because we are already publishing the references from in the user side itself. So it is very simple. It simply takes your relevant chunks and puts you the very nice generator response using OpenAI. And it keeps on trying until it is 5 times. Now over here, so what it eventually do over here is it stores and displays the information. So over here, if you can see, it stores the information which will be used to display the response messages. So now what this code is, and this st.rerun. So basically once the thing, then we just wait for it to run, and then another message can be added over there.
So, coming back to the next one, which is for message in the ST session state, what it does, it loops through the conversation history, because we are storing all our conversation history into the messages, and it loops through and then displays each messages, which is user message as well as the bot message. So it goes through the all the state which we in the current session. So if I refresh, it will be gone. If I refresh, it will be gone. But it is displaying the messages because it is already stored into into this particular current state. So if the references, because we also want to add the references. So if the references exist, and references are nothing but your chunks. If the references exists and the message references, if you see, into this case is nothing but the chunk. So if the references exist, then you can expand it, which is expander, and then you simply write all these references. And then you say something, which is over here. Say something. You need to add, so to continue the conversation. And then it is as simple. If the input message comes in, then you create an asynchronous task and run until complete, where you send a message while giving the input message. And when you call the send message function, it does all these function, and it keeps on doing it. It keeps on adding into message and into that current state. I hope it makes sense to you now. Now, in the final workflow, users enters a query in the chat input, and then what it does, it retrieves the most relevant chunks, and then they send them to OpenAI APIs along with the query to generate a response, and the assistant response, which is over here, the bot response, is displayed along with any references. So I hope you got the, it's very simple. We have already discussed. It's just that we have made a little bit advanced stuff, more efficiency centric and all. Manage tags. So this is very simple. I don't want to talk more in detail. So it's basically we have created a framework. We have given a position to delete a tag, and then we have created dialog, the decorator function, to a decorator to add a tag, where the function is that somebody can, the tag is the text input, and then you're calling the tags table into the database to create a new tag, and then you rerun it to show you the updated one, right? It is very simple. So you create a container, and then it should write it, and then you should give an ability to someone to delete it. It's very simple. I don't want to go in more detail because we have already took a lot of time. I thought I'll complete this project in 30-40 minutes, but I hope that you understood the tag systems. Is, you can see over here, I would appreciate, I have not gone through some of the code which was not too important for me to explain. It's your job. Please go ahead and go to GPT, copy and paste. Streamlit is very easy to know. Just copy and paste. Otherwise, it will take me another hour to explain you each and every line of Streamlit code. So I hope now it makes sense. And then what we do is nothing, is we are done. And if you come over here, then you have the chart with documents, manage documents, and the manage tags ready, which can be further used. Now I hope it makes sense. Now what we will do is we will finalize everything, and I will just make a final intro on what improvements can be done and what can be possibly the next set of course of steps for you into this project. Now what I want you to do is I want you to a little bit think about how you can make this project better, to actually put this into your resume. I can actually add multiple features, multiple functionality, but you should be the one who should you should think very creatively and eventually implement this project in a way that is more unique than what we have done over here. And this was on a major project which we have developed. Now what you can do, there can be multiple sort of what can you say, improvements which can be particularly added over here. For example, you can add a functionality to segregate chats. Maybe you can add a functionality to give some sort of analytics. You can add a functionality to enhance you can accept more multiple files, like images, like video files, so that it actually accepts such things. So you can also give instead of somebody writing the tags, you can give them the recommendation based on the document, a tax recommendation based on the document, and then you can eventually they can use the machine learning model to suggest tags based on the document content. Or you can add a tag search feature which can add functionality to search for documents using tags. And you can also improve more sort of in terms of improving and sort of trying out different embedding models and seeing what it works, improving on the prompts. You can also work on the autocomplete for the questions. You can talk about feedback mechanisms to make sure that how your users are interacting. You can also have this knowledge graphs so that
It can look very nice, and then you can also have the analytics, as I said, and then you can have the domain specific prompts, so that if somebody is coming from a climate, they have a different prompt. Somebody coming on different, they have a different prompt. And then somebody can come collaborate. You can also use fine-tune model, ensemble of the several models. Think about how you can do it. I would strongly suggest you to go through PGAI and pgvector. They have amazing integrations. Go through their platform, learn about it. I'll link more resources into the description down box below. It will be very easy for you to eventually go ahead. I wish you the best, and I hope to come to the next video with more advanced projects like this.
What we will do is we are going to talk about how we can upgrade our LexiChat models. So first of all, you have already built a functional LexiChat system with traditional methods like pgvector for embeddings and basic retrieval techniques where you're calling sort of OpenAI API calls to retrieve and generate the answer. So all this you have done it. But what if I told you that you were just scratching the surface? It was just the surface which you were scratching. You can make it much more faster, smoother, and smarter and production ready for handling millions and millions of queries efficiently. And that's what we are going to do into right now, is we are going to transform our LexiChat into faster, smarter, and production ready systems, and which will make your resume and your project looks way better than most of the people who are just relying on the basic systems. So in this section, we are taking LexiChat to the following levels. So far, just to recap what you have done, you have converted the documents which are split into manageable chunks for the processing, and then OpenAI embeddings are used for the chunk vectorization. And then you use the similarity search, pgvector similarity search to identify relevant chunks. And then LexiChat retrieves and presents answers based on the vector matches. That is what the retrieval and the generative model which we have built right now. But as system scales, we will face several challenges. We'll discuss about these challenges into greater detail in the next 1 hour of the videos, but I'll just talk in overview of the challenges which we'll face. The first challenge is the retrieval process will get slower and slower as the database grows. So if you search with the similarity search, this will keep on the latency, the efficiency of this will be decreasing a lot using pgvector. So there is something known as pgvector scale, which helps you to rectify this issue of even if the database becomes so large, it should be able to manageably, efficiently makes the retrieval process way better. Then embedding generations becomes again cumbersome. It's all about if you have the larger amount of database, everything will be an issue, whether it's search or whether it's even embedding generation. An overall system needs to become more cost effective and scalable. So if you have millions of rows, it may be that you get a lot of errors, something breaks down in the production, so a lot of issues will start to happen. And that's what we'll have to face, which is slower retrievals, manual embedding processes, architectural complexity, and cost efficiency. What we will do, we'll talk about each problem in greater detail as we discuss more about the improvements which we'll do in the next 1 hour. So if you don't understand, don't worry about it. Perfect. So what will be modified? The first is that we will address the scaling challenges, which is embedding generation. So what we will do, we will automate the whole embedding generation. We'll not talk about right now how we'll do it and why, what's, and hows. You'll get to know once we have the embedding generation. We'll use pgvector scale for efficient query handling using stream scan, and you'll see how efficient it would be when you use it, and you'll understand the problem over there itself. I'm not going to talk about the problem in greater detail right now, but we have discussed about the problem and the solution for each of the improvements which we'll be doing. We are also going to make sure that all the workflows for scalability and cost effectiveness are streamlined, and then we'll use something as PGAI chat completions for a direct database to OpenAI communication instead of any APIs or layers into it to remove any architectural complexity in there. So I hope these are some of the changes which will modify. If you have not understood any changes right now, don't worry. We have talked everything in detail. So the first improvement which we'll do is embedding generation, where we'll automate entire PGAI vectorizer. So what we were doing previously, we were simply going ahead and then we were asking OpenAI, calls OpenAI, and then probably we have to create, the OpenAI gives us embedding and then we store it into a database. Everything will be automated and you don't even have to call OpenAI. It's just your PGAI, PGAI vectorizer, which anytime the chunks is added, it automatically creates a new table and then adds it over there itself efficiently, which you don't have to do anyhow. It's just few lines of SQL code, which is way efficient and faster than what manual process could be.
Another one is faster retrieval. So instead of if you have millions of rows or millions of data into the databases, you don't have to use pgvector for that. Pgvector scale uses efficient indexing algorithm like screaming disk ANN and we have talked about these algorithms in greater detail. So if you don't understand, that's all right. And the last improvement which we'll do is instead of having a multiple layers of API calls directly to the OpenAI, we are going to integrate, we are going to use PGAI to automatically let database interact with the OpenAI to get its answers. That's it. So these are the few changes which we will do into our system, and we are going to start with our first change. Before that, we'll quickly set up a few things. I hope you have the installation guide. So let's quickly set up the few things before we start with our first improvement. So quickly we will set up our thing. Now before we go ahead and before you go ahead, I hope you have followed our installation guide PDF where we asked you to install the PostgreSQL, and then we asked you to install Docker, which is very important because we're going to use Docker for installation of the timescale setup. And then I have asked you to download the Python 3.8 and required libraries. So let's first of all go to the first step, which is nothing but making sure that you have the Docker compose file, which we have listed out here, is there. So what you should do, you should first of all go ahead and download Docker if you have not, and any Postgres GUI client. I have used Table Plus as a GUI client for Postgres. And then what you should do, you should download all the, you should first of all create a virtual environment. So the virtual environment is created by following. You can just go ahead and let me just show you the, I think we have already given the installation guide. So basically Python when LexiChat, and then what you should activate that virtual environment by source LexiChat bin activate. And once that virtual environment activated, you should install all the requirements from the libraries out there. Now, once that is ready, what you should do, you should go ahead and simply go ahead and we will now go to the Docker. Is that so? Let's quickly get these things ready. So now you have to set up this Docker compose.yaml, which is the name of this PGAI, and the services over here would be timescale. You don't have to worry about this. Is given by PGAI Docker image itself, so you don't have to worry about what is this. It's just for installation purposes. So we're going to install PG the timescale PG. Mine thing is PG16, Postgres 16, and then you have to replace all these placeholders with your thing. Your Postgres user, when you are setting Postgres as connections, you must be having all this: user, password, OpenAI API key, as well as your OpenAI API key, and then PG. So over here, this is the timescale where you're downloading the timescale stuff, and you have given the whole container name as a PGAI, where all the services will be downloaded. Timescale DB, where we are setting up first, and then the vectorizer worker, which is the PGI vectorizer, which we're going to use. Don't worry, we'll learn about it. PGI vectorizer, which you're going to use. Ignore everything. Over here, you just replace this with your informations and then OpenAI key. That's pretty much it. So once you do it, I'm going to quickly, change my thing. Okay. So I think I have this ready. I'm going to save it. And then what I'm going to do, you have to, let me quickly go ahead and delete everything from here so that yes, I'm going to delete it over here. Let it delete. Perfect. So there are no containers. So what you should do, you should come back to this terminal and then run this command, which is, I've just written it everything for you so that you don't have to, guys. Docker compose up d timescale db, right? So once you do that, it will automatically create something over here. So if you go to the container, you have timescale db running and it's going on, right? So that's the first command which you have to run, which is docker compose. Now what we'll do, we'll have to, because we need to run our Streamlit applications too. So you simply go to the some db.py and initial setup. So this may be uncommented. So please uncomment it. And then what we will do, we'll simply run this out first in Python. And I'm just going to do this. Okay, that's good. Now we'll run this. Let's see if it yields any error. So if you click on chat with documents, then only, and it says schema AI does not exist line. So the reason why it states, because we have not enabled our extensions into our database yet. So you go to the GUI extension and then you simply come over. So if you see, all the tables has been removed, right? So you have to write create extension and then select it and then run it. So it says the installation required extension, pgvector installing required extension. So it will install all the PGAI pgvector scale extension for it to work. And then if you now refresh it, it should be able to work now, right? So that's the first thing which you have to do. And then you come back, right? And then you come back and then you download your another service, which is your worker into this. So I'm not going to show it to you, but yeah, vectorizer worker. When you do it, you'll be having your worker also ready. So you see vectorizer worker is also running out here into your Docker. Your installation setup done from here. Make sure that you have enabled the extensions and everything so that your pgvector knows that, okay, this extension is there. And then now you can go ahead and follow the tutorial as it goes. So I hope you have also followed the installation guide and follow this setup to make sure that you have everything running in. So hey everyone, now the first thing or the first improvement which we will talk about is how we will go ahead and enhance our embedding creation processes. So previously what was happening is, first of all, what you were doing, we used to manually generate embeddings for our document chunks using OpenAI APIs. So what does the process really look like? That what we do, we first of all pass the document and split it into the chunks. So basically the bigger portion of the text used to be converted into the chunks, and then we used to use OpenAI API calls or PGAI for each chunk to generate embeddings of that particular chunk, right? And then what we used to do, we used to store those embeddings in the PostgreSQL column alongside the chunk. So if I could tell you what used to really happen, so let's say that you have this document chunks, and then you have the document ID, then the chunk of it, and then the embedding of it. That was used to happen, and it was more like a sort of the process where you first of all pass the documents. Once uploaded, you pass the document into the and then that gets converted into the chunks, and then the chunks eventually got called by OpenAI APIs using PGAI to generate embeddings, and then we used to store those embeddings into these particular documents. So this was our previous approaches. Now the problem with this is there are major problems, which is the challenges which comes across. So every time you upload a document, you have to write custom logic for chunking. So it has to go every time chunking, embedding generation, storing results. So it was every time you upload a document, it has to go through all those procedures, which is like a custom logic into this case. Now let's say there is a millions of chunks, not hundreds, thousands, millions of chunks, and very possible in the real world scenario, millions of chunks comes across. So for that, it is not scalable to add in a for loop approach and all. And then embedding generation was always prone to errors due to inconsistent chunking strategies. Then one time it is there, another time OpenAI behaves very differently. So the embedding generation was a very inconsistent processes, and also the storage was not optimized for embedding data. So it was more like, even if there's a millions of dimension rows, it used to get into the database, which is not optimized. So if you need to go and search it back, it used to take it might take us a hell lot of time, because if we see a millions of such examples or the rows out there. So these were the few of the problems with the older approach, which is manual embedding generation and the processes. So now we have something known as PGAI Vectorizer, which is again an open source extension of the timescale database. So what it eventually does, over here we have replaced the manual embedding process with the PGAI Vectorizer. So what it does, it automates everything with the best efficiency and with the best scalability, and keeping in mind of efficiency, scalability, optimizing costs, and all the specific details in terms of infrastructural level. So what we are doing in PGI, so what PGI does, it does whatever we have talked about: chunking, creation, and storage, but in very automated and efficient way. So what it does, PGAI, first of all, once it receives the document, it breaks your document into chunks using a built-in character. So of course it has a built-in character, we'll talk about it. And then what it does, it creates the embedding. It automatically calls the OpenAI model of your choice directly from PostgreSQL. You don't have to write the custom code here. PostgreSQL directly coordinates with the OpenAI to generate the embedding. And instead of keeping embeddings in the primary table, PGAI creates the different table. So now what I'll do, I'll quickly show you how does this work. So what eventually happens? So let's say that somebody comes over here and then we upload some document. Let me just quickly go through it. Manual processes. Yeah, the water cycle over here. So we have uploaded the documents out here, and what really ended up happening is this gets upload this documents gets uploaded into the database. So once you upload it, what really happens, it automatically creates the chunks, but over here it creates the new table, new view table, not the table which you can do anything, just for view is chunks as well as the embeddings. So that's what I said, it generates embedding for each chunk using the OpenAI. We have not created the new table, it automatically creates it. So because PostgreSQL is automatically interacting with the OpenAI to create the embeddings. We'll come to the code part, but I want you to realize the importance of it. So coming back to this, just give me a second. Yes. Coming back to this, what really happens is it automatically creates the chunk. Once the document is uploaded, it's everything automated and very efficient. It creates the chunks, then it creates the embedding directly from PostgreSQL, not from writing custom code, and then it has an optimized storage. So what does it really mean? It means that instead of keeping embeddings in a primary table, PGAI vectorizer stores them in a separate optimized column, which is in a view-based format, not something which you can do, and you don't have to create this, right? So let me quickly go and tell you in the code part how it exactly works. So previously we used to have this db.py, and then in db.py we used to create the document information chunks, and we used to have an embedding also, which is our one more text field where we used to create the embedding. So if you come over here, so this was a document information chunks, document ID, the content related to it, as well as the embeddings out of it. So that used to happen, but over here we are not doing it. So what we are doing, we are doing the initial setup, so which is very important. So just to make sure that you understand this very well, what you should do, you should first of all, we have the code and this will be commented. So you have to, in the first run, you have to uncomment it, because this is the only one setup you have to do only one time, so that your vectorizer, PGAI vectorizer gets activated. So what does it really mean to get activated? It means that so if the document is uploaded over there, every 5 minutes it will keep on coming and checking that whether the chunks are available or not, whether the document has been uploaded or not. If they are uploaded, then it automatically creates the chunk. So over here we need to do the setup. So any documents comes into the place, it should be able to automatically convert those new chunks, then embeddings, and then store it. Right, that is what the tables are. So we create a table, a db.create tables, and over here we are giving all the because we are creating this document table, tags table, document tags, and document information chunks as previously. And then we are executing, and then we are also making a new setup, which is the PGI vectorizer, where it automatically creates such things, where this is a SQL code. So it says select AI vectorizer, which is create vectorizer, and then we are creating the document information chunk. So what does it really mean, the document information chunk? The document information chunk over here really means that we need to take where to take the chunks from. We need to take the chunks from this source. So this is our source where we need to take the chunks from. And then what should be the destination? The destination should be this, the document information chunks embeddings. And that's what it really means, document information chunks embeddings. That's what the destination is. And then you have you have an embedding. Now embedding really means over here that the chunks which you've taken from the source, because this was the source which has been converted into the chunks, and now we convert those things into an embedding by calling pgai.embedding OpenAI. That's again which we have been doing using PGAI, and then we use the model of a choice, and we give the OpenAI API key. Okay, I hope that you have already run this Docker compose in your initial setup so that you can easily get your OpenAI API key. Now chunking, what does it really mean? Chunking means if the particular thing is big enough, so it automatically chunks also. It automatically chunks also. For example, if you have the source like 4 to 5 sentences, so it automatically chunks also by using the text splitter method of its own. Formatting means that, let's say that you have this embedding. So what it does, you can write chunk this just for the formatting purposes. Of course, we are not going to use it, so the chunk would be simple chunk. Please add my chunk. Otherwise, you can go ahead and add any sort of statement over here. So that's what the formatting means. So what it does, it simply creates this sort of setting where any documents which you upload, it should be able to automatically go over there and create the chunks if the source chunk is large enough, and then convert it into embedding and store it into the document information chunks embedding. And that's what it does, nothing else. So I hope that you really understood this, what PGAI AI vectorizer does. And I will talk a little bit about what is the difference between our old approach and the newer approach. The old approach, what it really was, that we used to do it everything manually, but now over here, what we are doing is automating it, which means that it is more simplified workflow. So we are literally, previously we were writing code, right, to chunk it off, and then we are writing code for taking the embedding. Over here, we are not writing any code, right? That's what the power is, and they are more efficient. So it's like you don't need to write custom chunking or embedding code anymore. It's more like a simplified workflow. And then you have the embeddings which are stored into a dedicated table optimized for vector data. So that is automatically created by PGAI, and everything runs with a single command, SQL command. So it saves time, it reduces any sort of errors, and it handles millions of chunks with a minimal effort into this case. Right? So I hope it makes sense, whatever PGAI vectorizer is. And now if you run it, so let's say that we have this particular thing, and what I'm going to do, I'm going to just do one thing. I'm going to delete this. So all the things will be also deleted. Let me just quickly show it to you. I hope so. Yes. So as you see, everything is deleted now. We'll go ahead and upload something, which is into this, our water cycle. Perfect. Let's run this. Let's wait for this to run. Perfect. And then what we do, we simply go over here and then we run this. So if you see, our initial setup was uncommented, which was uncommented. So it again creates the new vectorizer and tables and everything such like that. So it says that you have the embeddings right over there, the content, the chunk. So this was the content, and this was the chunk which was got from the content, right? And this was the content, this was the chunk. So of course we are taking the source, this as a chunks, the content, and then this is our source where our bigger file is converted into the smaller pieces, and then these pieces were given to the as a source to the embeddings where this is the content and this is the chunks. And then if you keep on uploading, so as you see, we have not written any code. So this is why there is the reason why we are using PGAI vectorizer. I hope it makes sense. I hope it really makes sense to you. Now what we'll do, we'll go ahead and do more improvements using pgvector scale. We are going to use PGAI more, and then we'll help you to make you understand much more better. Thank you so much. We'll see you in the next one. So now what we'll go ahead is talk about another problem, which is, let's say that if your data comes in millions and millions of rows, the problem of optimization, the problem of working with the larger data sets. Of course, I do not have that kind of a data set which I can show that how it really affects, but I will talk about some of the theoretical language in order to make you understand that what is the real problem. So the real problem is, so let's say that you are in a huge library with 1 million books, and you're looking for books that talk about space exploration. So that is a situation that you have a 1 million book into a particular library, and you want to take out the space exploration book. So how you will search? So I'm taking an example of pgvector. So we were using pgvector previously. So how you will use pgvector in terms of taking out space exploration books from those 1 million books. So basically what you'll do, you use a basic catalog that tells you which books mentions the space exploration
text. That's what, right? So you will go ahead and then you'll use a basic catalog that, okay, these segment of a book mentions about space exploration. But the only problem with this, that it is faster because you eventually get where the space exploration books are, but it only works if all the information fits into the small notebook, which means the catalog. So catalog might be a small notebook where, okay, at this point of time, this book is there, at this block, these books are there. So if the catalog is small and your information can fix into that catalog, then only it makes sense. If the catalog becomes too big, then it's also hard for you to find out, okay, let's first of all figure out the catalog thing. There might be millions of topics, so you try to find, okay, where it is. So if that gets too big, then that's where it slows down, that your searching capacity slows down. And that's what is the major problem which comes in. So to talk in a nutshell of, if you are in a book of a library where it has 1 million books and you're looking for the books that talk about space exploration, so basically you look at a basic catalog which is there and find out the book. But now if the catalog is too big, you'll have a hard time in finding the right first of all block to go in. So now over here, now let's say that if you don't use pgvector scale, so first of all, or pgvector, it is very time consuming because you need to manually search through all the chunks, millions of records. Traditional methods, which is scanning, going one by one, does not make sense. And even pgvector method of catalog is eventually slow down as the data size increases, right? And basic problems. So that's where the pgvector scale helps. So we have something called streaming disk ANN algorithm, which helps you to do the optimized search, which is one of the so pgvector scale is nothing but a complementary solution to pgvector, where it helps in one of the major problem, which is optimizing the search procedure for retrieving results if you search something. So I'm not going to go in detail about what streaming disk ANN does. So what it does in a nutshell, it's like, instead of flipping pages, finding one by one, or relying on memory catalog, what it does, it summarizes the catalog onto a disk, right? And it organizes the books in a way that helps find the related topics faster. I don't want to go into mathematical details on how it eventually does, but it stores the book summaries into disk, and which helps, and also it organizes the books in a way that it helps the find related topics faster and much more better, which is faster and relevant results. You can go, if you are more interested to know more about streaming disk N and how it helps, you can go ahead and learn from different sources. But we are using a disk-based scalability, disk-based storage to intelligently handle massive data sets, which helps to balance your accuracy and the speed, and also helps you to get faster and relevant results without scanning the entire data sets, or without looking at the catalog or big catalog if you have the huge data set. So I'm going to take one example of chatbot with pgvector scale. So pgvector scale is, as I said, is nothing but a complementary solution to the pgvector, where it helps to, what can you say? Where it helps to efficiently search. So let's say that the chatbot has to look through all the stored chunks of knowledge to answer a question. So some question was asked, and the chatbot has to look through all the stored chunks of the knowledge to answer. So if you use pgvector, it just goes to the catalog, the index, and then tries to find it. But now, if you have the millions of chunks, the catalog becomes big and the process slows down, and the relevant results also slows down. So the chunks which are stored onto disk, what it does is using streaming disk ANN. So now over here, chunks are not stored into some sort of Postgres state database. It's stored into a disk, into a particular format, which organizes them efficiently, right? And then what it does, it organizes via streaming disk ANN algorithm. Now let's say that if somebody asks, what is the tallest mountain on Mars? So pgvector scale, it finds the most relevant 5 to 10 chunks quickly. The reason why it is able to find 5 to 10 relevant chunks quickly is because the chunks are stored efficiently into a disk using streaming disk ANN algorithm. And then it saves time by skipping irrelevant chunks, and the chatbot gives you the exact numbers faster. Now, let's say I will take one example. I'll take one example of pgvector scale and how it eventually helps. So let's say that you're using, you have 1 million chunks, let's say 1 million books, and it takes 1 second to
check each chunk whether that particular question is related with the chunk or not. So the total time which will take for it to do is about 1 million seconds, which is about 11 days to find the answer to a single question. Now with PG vector scale, the smart catalog which we have is the disk ANN, which narrows it down to the top 10 chunks into the milliseconds. So it just gives you the top 10 chunks instantly, and then what it does, it takes less than 1 second to give you the answer. So that's why PG vector scale is way more faster, way more efficient, and improved accuracy in terms of this. So what we will do is I'll quickly go make you through some of the code changes which we did. There's no specific code changes. This is very simple code changes which we did, which is not so hard also to understand. So over here we are adding something known as set disk ANN query score. So we are making in db.py, we are setting this set db and disk ANN query score. So what does it help? These are key parameters for the disk ANN. We are obviously using PG vector scale. I hope you have installed and enabled the PG vector scale so that it automatically stores the chunks into a disk sort of setting. But these are key parameters for the PG vector scale. So the first one is the setting up the query score. So what it helps, this parameter helps balance accuracy and performance during queries. So let's say if you have lower query score, which means it will be faster but less accurate retrieval, which is less accurate information. But if you set more high query score, it is slower but higher accuracy into this case. So this is just a definition so that we can use this command to use this into our when we retrieve the information. So let's quickly go and talk about where we are actually retrieving the information. I'm gonna go over here and then come to this chat with documents and this one. Yeah. So over here we are sending the messages, but over here when we send the message, it is a generative phase where we are first of all retrieving the information. So over here we call that function, we call that particular function which we have made and give the 100 as query score, which maintains a good balance between accuracy and score. Then it sets the OpenAI key so that we take the results from the OpenAI, and then it executes the command. And you don't have to do literally anything. You just have to enable the PG vector scale and set the scores. That's pretty much it. And that's what the PG vector scale will help you to do everything very efficiently. You will realize this importance when you work with the millions of data sets, how quick it is. And then you can compare with the PG vectors to see how small it is. So what it does, it result is select the content from the document information chunks, and then you create an embedding for the question, and then you take out the top 5 chunks out of it. Right? And then you simply go ahead and then take the red chunks, and then you, as we have talked about, everything in detail remains the same. Nothing changes. Just you need to set the disk ANN score over here. That's pretty much it. So I hope it makes sense. I hope it really makes sense. Now, if I talk about in a nutshell how eventually PG vector scale helps, without PG vector scales, SQL query scans all the rows, taking longer to execute, but with PG vector scale, it uses disk ANN indexing for cosine similarity to find the top matches in milliseconds. So it's all about optimization, making it great. So if you use this PG vector scale into your project, your project will be way more, advanced, because it is able to handle even millions of rows, columns, and stuff like that, data in a matter of no time. I hope it makes sense. Now what we'll do, we'll go ahead and talk about another improvement, which is using PGAI for the chat completions. Right now we are directly calling the OpenAI for it. Now what we will do, we'll go ahead and use PGAI to Postgres directly. So in case of PGAI embedding generation, Postgres directly talking with OpenAI to get the embedding. So it is not, we are not writing custom codes. In the same way, over here, the Postgres will directly talk with the OpenAI to take the chats completions to make it faster, efficient, and more accurate. So hey everyone, we're going to talk about our another improvement which are doing it very majorly and which makes your project super duper amazing is chat completion. So basically generative, where previously we were using PGAI to create the embeddings directly from the OpenAI. We are going to use PGAI chat completions method to generate an answer, basically generative model to directly from the OpenAI interacts with the PostgreSQL. So what is the traditional approach right now? So the traditional approach is that you need to write a separate layer of code in Python or JavaScript or similar languages to handle OpenAI calls. So that should interact with OpenAI, and then OpenAI gives some result, and then you take out and you format it in a way and all those things. Now switching between the app layer and database, adds delays into it. And that's another problem, that there are multiple layers and it creates a higher latency problem, and it makes it more prone to errors, makes it more prone to system failures. That's why you were saying that if you're running previously, you're retrying. So those things happens a lot. So that's what we eventually give something known as PGAI. So you write code in Python or JavaScript to call the OpenAI API, and then the API handles keys, request information, it retries and responses in your application layer, and then it stores and retrieves separately from the database, adding complexity, which is very extensive. So first of all, it calls it APIs retries it, makes sure that you get an answer, and then it separately stores the information. Now, these are the major problems when you actually go to the extensive large scale databases or workarounds and all. So with PGAI chat applications, what it really happens, the database handles everything internally. So let's say that you have an database, so it happens everything internally, which is like embedding generation, which we talked about, the PGAI embedding generation, the retrieval of the chunks, and the response generation via OpenAI. And this happens everything inside it, where PostgreSQL database directly interacts with the OpenAI to actually get an answer towards it and stores the answer into the particular database without having any layers in between, making it more faster and efficient and much more better. So coming back to another one is I want to talk about first of all this one, which is generate chunks. So we were using OpenAI embed to generate the matching chunks, but over here what we are doing, we are generating the chunks, where what we are doing, we are giving the PDF, and then what we are asking, previously we were calling an OpenAI API to reach out and then try to give the whole bunch of text and then give me the prompts. If you see over here, the system prompts. So if I go over here, constants. So this is create fact chunks. Create an expert text analyzer, take any text and analyze it, create multiple facts out of it. So previously we were calling an API to do it. Now what we are technically doing, we are calling an OpenAI, which once the document is uploaded, internally interacts with the OpenAI to generate the response. Basically, you're calling select all the responses, and this is the method, which is ai.openai.chat complete. This is the model which you have to use, and the system and the user, and over here you create fact chunks, which is the instructions given to the system, and then PDF text, which is on which the instruction should be followed, and then we fetch everything. So this happens, this particular PGI makes it very efficient, much faster and better than all. So this is what one of the example is. And then we have another one, which is where we are generating the matching tag. So basically, previously, again, we were giving the text, we were giving all the tags out there, the PDF text, and then we were asking them to generate the matching tags. Over here, we are doing the same, but over here, we are calling this ai.openchat applications using this model, and everything remains the same. And that's what PGI is so powerful that you don't need to really add any layers. We literally removed all the layers from it, and it directly interacts internally in the databases. So over here, you're seeing that I'm executing a SQL command. So instead of going to the table plus, over there says GUI, I'm over here doing everything straight on over here. Then, particularly over here, you have something known as so with these were retrievals, where you're using PGAI to retrieve the stuff out there, which is chunks and your tags, which we have to match with. And embedding is already generated using PGAI vectorizer, which is another one extension which we talked about. Now over here, we are in generate the message, which is send the message. Instead of you calling an API to do it, you're saying select OpenAI and then use GPT-4a and then system. We are giving the messages and then we're storing it. So everything remains the same. Over here, we're literally calling PGAI to generate the answer. So which it happens internally, everything on its own. So to talk about it, how exactly it works, it's a built-in integration. So if you have seen, we have installed and enabled the PGAI extension. So PGAI connects with the PostgreSQL directly to OpenAI's chat API, and then it generates the responses using structured SQL queries, which we have did right now. And it handles, as I said, chunk embedding everything very efficiently, and it delivers as soon as possible, which is real-time responses. So That's why the PGAI worked a lot. So we have talked about this in great detail about PGAI, and PGAI is a very powerful library to help you do that, to generate embeddings, directly interacting with PostgreSQL and OpenAI without anyone in the middle. I hope it makes sense, and I really hope that all these improvements you will do it, and that makes your project much more better, much more powerful, and probably this might get you something. So what we will do, we'll finalize our stuff into our next call. So into our next video, and that was it, where we literally used pgvector scale for faster, PGAI for automatic chat completions, and pgvectorizer for a automatic embedding creation. I hope it makes sense. Let's catch up in the next one.